In March 2025, Chinese scientists announced a discovery that would rewrite our understanding of life on Earth. At nearly 11,000 meters beneath the Pacific Ocean, in a realm of crushing darkness and unimaginable pressure, they found not emptiness, but abundance. A thriving chemosynthetic ecosystem, the deepest ever documented, pulsing with strange life in conditions that should be utterly sterile. Even more astonishing, 89.4% of the microorganisms they collected were completely unknown to science, species that had never been cataloged, never been imagined, never even been suspected to exist. This was not just another scientific expedition. It was proof that the deepest place on our planet is still a frontier as alien and mysterious as any distant moon, hidden not light years away in space, but just 7 miles straight down from the surface of our own oceans. This discovery should not have surprised us, and yet it did. We live in an age where rovers crawl across Mars, where telescopes peer into galaxies billions of light years distant, where satellites can read license plates from orbit and track storms on Jupiter with precision. We have mapped the surface of Venus through its choking clouds and sent probes beyond the edge of our solar system into interstellar space. Our technology has given us the illusion of total knowledge, the comfortable belief that Earth itself holds no more secrets. But the Mariana Trench, a scar in the Pacific stretching more than 1,500 miles and plunging deeper than Mount Everest is tall, quietly exposes that belief as a beautiful lie. Despite all our satellites and sensors, despite decades of oceanographic research, we have explored less than 5% of the deep ocean, and the trench itself remains one of the least understood places on the entire planet. The paradox is almost embarrassing. We know more about the topology of Mars than we do about our own seafloor. High-resolution images from orbit have mapped every crater and canyon on the red planet, yet vast stretches of the Mariana Trench exist only as blurry approximations, rough sketches stitched together from distorted sonar echoes that may be off by dozens of meters or more. When Victor Vescovo piloted his submersible to the bottom of Challenger Deep in 2019, he became only the 4th person in history to reach that point, and his dive added crucial data to our understanding. But even with modern technology, even with the most advanced materials and engineering, his time at the bottom was measured in hours, not days. He could see only what his lights revealed within a few meters, film only a tiny fraction of the landscape, and collect only a handful of samples before the vehicle had to begin its long ascent back to the surface. It was a triumph of human ingenuity, but it was also a reminder of how little we can truly see and do at such depths. The reason for this limitation is not lack of funding or interest, though both are certainly factors. The real barrier is physics itself. The Mariana Trench is a place where the familiar rules of the surface world break down one by one, replaced by extremes that challenge every assumption engineers make about materials, energy, and design. At the deepest points, the pressure reaches over 16,000 pounds per square inch, more than 1,000 times the atmospheric pressure we experience on land. To put that in perspective, imagine balancing a fully loaded commercial airliner on your thumbnail, and you begin to approach the forces pressing in from every direction at the bottom of the trench. This pressure does not simply squeeze objects. It deforms metal, compresses gases, finds microscopic flaws in welds and seams, and exploits them ruthlessly. Submersibles must be built like fortresses, yet even the strongest sphere of titanium or specialized steel can only withstand so many dives before metal fatigue begins to whisper warnings that are invisible to the human eye. Pressure is only the first challenge. The cold at those depths is profound and relentless, hovering just a few degrees above freezing. This is not the refreshing chill of a mountain stream, but a bone-deep cold that drains energy from batteries, stiffens seals and lubricants, and slows the chemical reactions that power electronics. In the Mariana Trench, a battery that performs flawlessly on the surface may lose 30 to 50% of its capacity, and every system aboard a submersible, from lights to thrusters to cameras, must compete for that dwindling power. The cold also interacts with the extreme pressure to create water that behaves almost like a different substance, denser and heavier than the seawater near the surface, forming pockets and layers that affect buoyancy in unpredictable ways. A vessel that hovers smoothly at one depth may suddenly begin to sink when it drifts into a slightly colder or saltier layer, forcing constant adjustments and careful management of ballast. Then there is the darkness, a blackness so complete that it defies ordinary description. Sunlight, which floods the surface of the ocean with brilliance, cannot penetrate more than a few hundred meters before it is absorbed entirely, swallowed by water molecule after water molecule. Red wavelengths disappear first, within the first few dozen meters. Oranges and yellows follow, then greens, until only the faintest blue remains, and then even that fades into nothing. By the time a submersible descends past 1,000 meters, it has entered a realm where natural light has not existed for millions of years, a world shaped entirely by darkness. The most powerful LED arrays, glowing with thousands of lumens, can only carve out a narrow bubble of visibility, perhaps 3 to 5 meters at best. Beyond that circle, the abyss presses in, a wall of black that absorbs every photon. Cameras can only film what the lights reveal, and what they reveal is a tiny, intimate slice of a landscape that stretches for hundreds of kilometers in every direction. This limitation turns exploration into a painstaking process. Imagine trying to map an entire continent by walking through it at night with a single flashlight, able to see only the ground directly at your feet, and you begin to understand the challenge. Even advanced sonar, which sends pulses of sound downward to map the seafloor, struggles in the trench. Sound, which should travel in clean, predictable lines, is bent and distorted by the layers of water it passes through, each with slightly different temperature, pressure, and salinity. Cold brine, denser and heavier than the water above, acts almost like a veil, slowing and scattering the sonar pulses. The steep V-shaped walls of the trench reflect sound away from the ship, creating shadows in the data where entire regions simply vanish. What should be a precise measurement becomes an approximation, a best guess stitched together from thousands of faint, blurred echoes. Yet, despite all these obstacles, life has found a way to thrive in the Mariana Trench, and that is perhaps the most astonishing part of the story. The recent discoveries from the MEER project, a comprehensive study that ran from 2021 to 2025, revealed an ecosystem of staggering complexity. Chinese researchers conducted 33 dives using the Fenduzi submersible, collecting over 1,600 sediment samples from depths ranging from 6,000 to nearly 11,000 meters. What they found was not a barren wasteland, but a hidden world of microbial life, organisms that feed not on sunlight, but on chemicals seeping from the Earth's crust. These chemosynthetic communities build entire ecosystems in complete darkness, using hydrogen, methane, and sulfur compounds as their energy source. Of the thousands of microbial species identified, the vast majority were completely new to science, genetic lineages that have evolved in isolation for eons, adapted to pressures and conditions that would obliterate any surface organism in an instant. This is not just a curiosity for biologists, it is a fundamental challenge to our understanding of the limits of life itself. If complex ecosystems can flourish at the bottom of the Mariana Trench, where pressure is crushing, cold is relentless, and darkness is absolute, then what other extreme environments on Earth or beyond might harbor life? The discovery suggests that our planet still holds vast reservoirs of biodiversity that we have never touched, never sampled, never even suspected. It suggests that the deep ocean is not a desert, but a wilderness as rich and strange as any rainforest, only far more difficult to reach. Every dive into the trench brings back samples that rewrite textbooks and raise new questions, and every new organism discovered hints at the millions more that remain hidden in the darkness. The technology required to reach these depths is itself a marvel of engineering, but it is also fragile and expensive. The Fendosia submersible, which set multiple records during the MEER expeditions, can carry 220 kilograms of samples and operate at the seafloor for up to 6 hours. That may sound generous, but in the context of the trench's vast expanse, it is a fleeting visit. Every minute must be carefully planned, every movement calculated, every sample chosen with precision, because once the power begins to fade or the life support systems strain, there is no room for error. The ascent back to the surface takes hours, and any malfunction at depth can turn a scientific triumph into a disaster. This is why, despite billions of dollars spent on ocean research, fewer people have visited the bottom of the Mariana Trench than have walked on the moon. So why does this matter? Why should we care about a place so remote and so hostile that it seems almost irrelevant to daily life? The answer is that the Mariana Trench is not just a geographic curiosity. It is a lens through which we can examine the limits of human knowledge and capability. It reminds us that exploration is not a relic of the past, not something finished and filed away, but an ongoing challenge that continues to push the boundaries of what we can achieve. It shows us that the Earth still holds mysteries as profound as any in the cosmos, and that understanding our own planet may be just as difficult and just as important as reaching for the stars. The trench is a humbling counterpoint to our technological confidence, a place where nature still sets the rules and where we are still, fundamentally, visitors. As we move deeper into this story, each layer of the trench will reveal a new kind of resistance, a new obstacle that our machines must overcome or work around. We will explore how sonar bends and blurs in the cold, dense water. We will examine how pressure reshapes metal at the molecular level, exploiting weaknesses that are invisible until it is too late. We will see how darkness and cold conspire to drain power and limit visibility, turning every dive into a race against time. We will discover how the trench's geology, constantly shifting and folding under the slow-motion collision of tectonic plates, creates a landscape that refuses to stay still long enough to be mapped with certainty. And we will meet the strange life forms that have made this extreme environment their home, organisms that challenge every assumption about where and how life can exist. But this opening is not just about obstacles. It is also about wonder, about the irresistible pull of the unknown, and about the quiet courage of scientists and engineers who continue to push into the abyss despite the risks and limitations. The Mariana Trench is a reminder that the greatest adventures are not always the ones that take us farthest from home, but the ones that take us deepest into the mysteries that have always surrounded us. It is a place where every answer leads to 10 new questions, where every dive brings back evidence of things we never imagined, and where the boundary between the known and the unknown remains as sharp and as compelling as ever. This is the story of why we cannot yet truly explore the Mariana Trench, and why that failure, paradoxically, makes it one of the most important frontiers left on Earth. To understand why the Mariana Trench resists exploration so stubbornly, we must first understand what it actually is, not just as a depth on a chart, but as a living geological wound carved into the planet's surface by forces so vast and so patient that they operate on timescales human minds struggle to grasp. The trench is not a static feature, not a simple hole that was dug once and left behind. It is an active scar, constantly being reshaped by the slow, grinding collision of tectonic plates that has continued for tens of millions of years and shows no sign of stopping. Every year, the Pacific plate slides beneath the Philippine plate at a rate of 5 to 10 centimeters, a movement so gradual it is invisible to the human eye, but relentless in its power. This process, called subduction, is what creates the trench, folding the seafloor downward like fabric being pressed into a crease, and it is also what makes the trench such a difficult, and unpredictable place to study. The recent MEER project, which ran from 2021 to 2025, represents the most comprehensive attempt ever made to study the trench's ecosystem and geology as a unified whole. Chinese scientists conducted 33 dives using the Fenduzi submersible, a vessel capable of withstanding the crushing pressures at depths approaching 11,000 meters. Over the course of these expeditions, they collected 1,648 sediment samples from a vertical range spanning nearly 5,000 meters, from the relatively shallow Hadal zone at 6,000 meters down to the very bottom of Challenger Deep. This was not just sample collection, it was an attempt to read the trench like a book, layer by layer, to understand how its geology shapes its chemistry, how its chemistry shapes its biology, and how all these factors interact to create an environment unlike any other on Earth. What they found was a landscape far more complex than earlier models had suggested. The Mariana Trench is often described as a simple, V-shaped cut in the ocean floor, and from a distance, that description holds. The walls do rise steeply on either side, leaning inward like two immense slopes pressed close together, guiding everything downward toward a narrow floor. But within that broad structure lies a hidden architecture of basins, ridges, and pockets that complicate every attempt to map or understand it. Challenger Deep itself, the deepest part of the trench, is not a single point, but a cluster of separate depressions, each one a small basin where the seafloor dips even lower. These basins are separated by rises in the floor that sit only slightly higher, creating a landscape that looks less like a smooth valley and more like a series of interconnected pools, each with its own depth, its own sediment composition, and potentially its own isolated communities of life. This complexity creates a fundamental problem for anyone trying to study the trench. When sonar pulses are sent down from ships on the surface, they return with measurements that suggest one basin is the deepest, but a few kilometers away, another basin may be just as deep or even deeper, depending on how the measurements are interpreted. The differences can be subtle, sometimes only a few meters, but in the world of deep-sea exploration, those few meters matter. They determine which location gets labeled as the absolute deepest point on Earth, and they also determine where expeditions focus their efforts. But because the measurements themselves are uncertain, shaped by the way sound bends and scatters through layers of cold, dense water, the title of deepest point shifts slightly with each new survey. What appears to be the record holder today may be surpassed by a shallow dip nearby tomorrow, not because the seafloor has changed, but because our instruments have finally resolved details they missed before. The trench's shape is a direct consequence of subduction, but the details of that shape depend on factors that are still not fully understood. As the Pacific Plate descends beneath the Philippine Plate, it does not do so smoothly or evenly. The plate is not a uniform slab of rock. It carries with it seamounts, ancient volcanoes that have long since gone extinct and sunk beneath the waves. It carries fractures and faults, weak zones where the rock has been stressed and broken over millions of years. When these features reach the subduction zone, they complicate the geometry of the descent. A seamount being dragged downward can create a bulge or a depression in the trench wall. A fault line can redirect stress, causing the seafloor to buckle or fold in unexpected ways. The result is a landscape that is far from uniform, a mosaic of features that change over distances of kilometers or even meters. This constant motion also means that the trench is never truly still. Micro-earthquakes, too small to be felt by anyone on the surface, ripple through the trench hundreds or even thousands of times per year. These quakes are the sound of the Pacific Plate grinding its way downward, of rock slipping past rock, of stress being released in sudden bursts. Each tremor sends vibrations through the water and the sediment, stirring up clouds of particles that can linger for hours or even days. For a submersible operating near the seafloor, these events create hazards that are difficult to predict or avoid. A sudden cloud of sediment can reduce visibility to zero, forcing cameras to shut down and navigation to rely entirely on instruments. A larger quake, though rare, can trigger underwater landslides, sending tons of sediment cascading down the trench walls and burying anything in their path. The sediment itself tells a story of time and motion. Over millions of years, particles have drifted down from the surface, settling layer by layer onto the trench floor. These particles come from many sources: the remains of plankton and other microscopic organisms that lived and died in the sunlit waters above, dust blown from distant continents, volcanic ash from eruptions that occurred long before human civilization began. Each layer is a record of the past, and scientists can read these layers like the rings of a tree, tracing changes in ocean chemistry, shifts in climate, and even the timing of ancient earthquakes. But the sediment is not just a passive archive. It is also a medium that shapes the trench's environment. Thick layers of soft sediment can insulate the deeper layers below, slowing the transfer of heat from the Earth's interior. They can trap chemicals and nutrients, creating pockets where life can concentrate, and they can obscure the underlying rock, hiding the true structure of the trench beneath a blanket that is itself unstable and prone to shifting. Beneath the sediment lies the bedrock, the compressed and deformed remnants of the oceanic crust that has been folded downward by the force of subduction. This rock is not the solid, unchanging material we imagine when we think of stone. It is under immense stress, squeezed and heated by the weight of the overlying water and the friction of the descending plate. In some places, the rock has fractured, creating faults and fissures where fluids can seep upward from deeper in the earth. These fluids are rich in chemicals like hydrogen sulfide, methane, and hydrogen, and they provide the energy that fuels the chemosynthetic ecosystems discovered by the MEER project. Where these fluids emerge, life clusters, building communities that depend not on sunlight but on the chemistry of the planet's interior. This connection between geology and biology is one of the most important discoveries to come out of recent trench research, because it suggests that the trench is not just a physical feature, but a living system, where the slow motion of tectonic plates directly shapes the possibilities for life. The V-shaped profile of the trench creates additional challenges for exploration. Unlike a broad, flat plain where a submersible can roam freely, the trench's steep walls constrain movement and limit options. A vessel descending into the trench must navigate carefully, avoiding the walls while also managing its buoyancy in water that changes density with depth. The floor itself is narrow, often just a few kilometers across, and in some places even narrower. This means that any survey or sampling mission has to operate within a confined space, unable to range widely without risking collision with the walls. The walls themselves, though they might seem like stable features, are not always safe to approach. Loose sediment clings to the slopes, and a slight disturbance from a passing submersible or a minor tremor can send it sliding downward in a slow-moving cascade. The trench also interacts with the ocean in ways that are still being studied. Cold, dense water sinks into the trench from the surrounding deep ocean, pooling at the bottom and creating a distinct water mass with its own temperature and salinity profile. This water is some of the oldest and coldest in the entire ocean, having spent decades or even centuries circulating through the deep before finally settling into the trench. It carries with it dissolved oxygen, nutrients, and particles from distant regions, connecting the trench to the broader ocean system. But it also creates boundaries within the trench, layers where the water's properties change abruptly, and where those changes affect everything from the behavior of sound to the distribution of life. Understanding these water masses and how they move is crucial for interpreting the data collected by sensors and instruments, because the physical environment of the trench is not just about pressure and temperature. It is about gradients, boundaries, and the subtle ways that different layers of water and sediment interact. The complexity of the trench's geology means that even the most advanced mapping technologies can only provide a partial picture. Multi-beam sonar, which sends out fans of sound across wide angles to capture thousands of depth measurements at once, works well in shallower waters where the geometry is simpler and the signals return cleanly. But in the trench, the steep walls reflect sound away from the ship. The narrow floor creates shadows in the data, and the layers of water with different densities bend the sound paths in unpredictable ways. The result is a map that is accurate in some places, but vague or missing in others, a tapestry woven from approximations where entire features may be hidden, simply because the sound could not reach them or return in a way that the instruments could interpret. Every survey adds new threads to this tapestry, but the full picture remains elusive, a goal that will require many more years of patient work. This is the geological reality of the Mariana Trench, a landscape shaped by forces that operate on timescales of millions of years, but also by events that occur in seconds, from earthquakes to landslides to the slow drift of sediment clouds. It is a place where the solid earth is in constant motion, where the boundary between the surface and the interior of the planet is thin and active, and where every feature, from the smallest ridge to the deepest basin, tells a story of stress, deformation, and adaptation. Understanding this geology is not just an academic exercise. It is essential for planning any exploration, because the shape of the seafloor determines where a submersible can safely land, where samples can be collected, and where instruments can be placed. It also shapes the distribution of life, because organisms in the trench are not randomly scattered, but concentrated in specific locations where the geology creates favorable conditions, where fluids seep upward, where sediments accumulate, or where currents bring nutrients. As we prepare to descend further into the details of exploration, this geological foundation becomes the stage on which all the other challenges will play out. The trench's shape affects how sonar works, how pressure builds, how light is absorbed, and how energy is managed. It is the reason why navigation is so difficult, why mapping is so incomplete, and why every dive must be planned with such care. The Mariana Trench is not just deep. It is dynamic, complex, and unforgiving, a place where the Earth's crust is being actively reshaped, and where every attempt to understand it must account for motion, uncertainty, and the limits of what our instruments can see. With this geological framework in mind, we can now turn to the first of the technical barriers that makes true exploration so difficult: the problem of seeing in a place where even sound struggles to find its way. With this geological framework in mind, we can now turn to the first of the technical barriers that makes true exploration so difficult: the problem of seeing in a place where even sound struggles to find its way. The trench's complex shape, its steep walls, and its narrow floor are not just physical features. They are obstacles that actively interfere with the tools we use to understand them. For most of the ocean, mapping the seafloor is a relatively straightforward process. Ships drift across the surface, sending pulses of sound downward, and those pulses bounce back, carrying information about the depth and texture of the bottom. This technique, called sonar, has been refined over decades into a sophisticated science, capable of revealing underwater mountains, valleys, and plains with remarkable clarity. But in the Mariana Trench, sonar encounters a gauntlet of challenges that turn a straightforward measurement into an act of educated guesswork. Sound is the only tool we have that can reach the trench from the surface without requiring a direct physical connection. Light cannot penetrate more than a few hundred meters, and radio waves die almost immediately in seawater, absorbed by the very molecules they are trying to pass through. That leaves sound as the sole messenger capable of traveling the 7 miles down to the seafloor and back again. Sonar systems exploit this by sending out pulses, usually in the form of focused beams or broad fans, and then listening for the echoes. The time it takes for a pulse to return tells us the distance, and the strength and shape of the echo can reveal details about the seafloor's composition and texture. In shallow or moderately deep water, this method works beautifully, producing maps detailed enough to guide submarines, locate shipwrecks, and plan undersea construction projects. But below 6,000 meters, where the Hadal zone begins, the rules change. The first problem is pressure. At the depths of the Mariana Trench, the water is not the same substance we know at the surface. It is compressed by the weight of everything above it, squeezed until its molecules pack closer together and its density increases significantly. This denser water changes the speed at which sound travels, slowing it down in ways that are difficult to predict, precisely because the density itself varies with depth. A sonar pulse sent from the surface does not move through a uniform medium. It passes through layers, each with slightly different pressure, temperature, and salinity, and each of these layers bends the sound path slightly, like light passing through a prism. By the time the pulse reaches the trench floor and returns, it has been stretched, softened, and deflected so many times that the signal arriving at the ship is weaker and less precise than it was when it left. Temperature adds another layer of distortion. Near the surface, the ocean is warmed by sunlight, and this warmth creates a relatively homogeneous layer where sound moves quickly. But as a pulse descends through the thermocline, the rapid drop in temperature slows the sound and bends its path downward. Below the thermocline, the water is cold, hovering just a few degrees above freezing, and this cold is not uniform. Subtle variations, sometimes just fractions of a degree, create pockets and layers where sound behaves unpredictably. A pulse that should travel in a straight line begins to curve, guided by gradients of temperature that act almost like invisible lenses. These curves are small, but over a distance of 7 miles, small deviations accumulate into significant errors. A sonar reading might place a feature several meters away from its true location, or miss it entirely if the sound is bent away from the sensor's listening path. Salinity complicates the picture even further. The deep waters of the Mariana Trench are filled with brine that is slightly saltier than the water above, carried by slow currents that have wandered across the Pacific for decades before settling into the trench. This brine is denser and heavier, and it forms distinct layers and pockets within the water column. When a sonar pulse encounters these layers, it slows down even more, and the boundary between water masses can reflect or scatter the pulse in unpredictable directions. The result is that some areas of the seafloor return strong, clear echoes, while others return only faint whispers, or nothing at all. Mapping software attempts to compensate for these effects by modeling how sound should behave based on known temperature and salinity profiles, but the ocean rarely conforms exactly to the models. Small, unmapped currents or temporary shifts in water mass properties can alter the path of a pulse by meters, turning what should be a precise measurement into an approximation. Cold brine, in particular, acts almost like a veil draped over the deepest parts of the trench. This water is not just cold, it is ancient, some of the oldest water in the entire ocean, and it has accumulated dissolved minerals and salts over its long journey. Its density is several percent higher than the water above, enough to create a distinct acoustic barrier. Sonar pulses entering this layer are absorbed more quickly, their energy dissipating as the sound waves push against the tightly packed molecules. The pulses also scatter, bouncing off suspended particles and microscopic gradients in a way that spreads their energy over a wider area. By the time the pulse reaches the seafloor and begins its return journey, it is so weakened that the echo arriving back at the ship may be barely distinguishable from background noise. In some cases, the echo is lost entirely, swallowed by the water and leaving a blank spot in the data. The steep V-shaped walls of the trench add a geometric challenge that compounds all the acoustic problems. When a sonar pulse strikes a flat or gently sloping seafloor, it reflects directly back toward the source, making it easy to detect and measure. But when a pulse hits a steep wall, it bounces off at an angle, deflected away from the ship, and lost into the surrounding ocean. This creates long stretches of missing information, like pages torn from a book. The narrow floor, hidden between towering slopes, becomes especially difficult to trace. Even when the pulse manages to reach the bottom, the return signal may be too faint to interpret, blurred by all the layers it has passed through, and distorted by reflections from the walls. The result is a map that looks smooth and continuous in some places, but ragged and uncertain in others, with entire sections that remain blank or filled in with estimates based on nearby measurements. Multi-beam sonar, The most advanced form of acoustic mapping attempts to solve some of these problems by sending out fans of sound across wide angles, capturing thousands of depth measurements at once. In coastal waters or on the continental shelf, this system can create maps so detailed that they reveal individual boulders and subtle changes in sediment type. But in the Mariana Trench, the beams spread too widely as they descend, losing focus and resolution. Each beam must travel through the same distorting layers of water, and by the time they reach the trench floor, they have diverged so much that the returned echoes overlap and interfere with one another. Sorting out which echo came from which beam becomes a complex task, and the software must make assumptions about how the sound traveled, assumptions that are not always correct. The deeper the trench, the worse this problem becomes, until the map produced is less a photograph and more a rough sketch. This limitation affects not just the creation of maps, but also the planning of dives. When a submersible is preparing to descend into the trench, the crew relies on sonar data to choose a safe landing site, to identify features of scientific interest, and to avoid hazards like steep drop-offs or unstable sediment. But if the map itself is uncertain, if entire regions are poorly resolved or missing, then every decision carries additional risk. A flat area on the map might turn out to be a slope in reality. A promising location for sampling might be inaccessible due to terrain that the sonar never detected. This uncertainty forces explorers to operate with caution, descending slowly and relying on the submersible's own short-range sonar to navigate the final approach. It also means that much of the trench remains not just unexplored, but unmapped in any meaningful sense, hidden behind the limitations of the tools we use to see it. Recent advances in technology offer some hope for improvement. In 2025, the National Oceanic and Atmospheric Administration began developing artificial intelligence systems designed to analyze sonar data in real time, identifying patterns and features that human operators might miss, and compensating for distortions caused by water properties. These AI systems are trained on vast datasets from previous surveys, learning to recognize the signatures of different seafloor types and to distinguish true echoes from noise and artifacts. The goal is to create maps that are not just more accurate, but also more complete, filling in the gaps and uncertainties that have plagued deep ocean mapping for decades. Early tests have shown promise, with the AI able to detect subtle features in noisy data and even predict the likely structure of unmapped regions based on the patterns observed nearby. But even with artificial intelligence, the fundamental physics of sound in water cannot be changed. No matter how sophisticated the analysis, a sonar pulse must still travel through layers of cold, dense brine, must still contend with pressure that alters its speed, and must still return through a medium that absorbs and scatters its energy. The AI can improve interpretation, can reduce errors, and can help prioritize where to focus limited survey time, but it cannot make the ocean transparent. The Mariana Trench will always be a challenging environment for acoustic mapping, a place where the water itself conspires to hide details and introduce uncertainty. This means that true, comprehensive mapping of the trench will require not just better software, but also new approaches. More ships spending more time on station, autonomous vehicles equipped with their own sonar systems operating closer to the seafloor, and perhaps entirely new technologies that can see through the water in ways we have not yet imagined. The gaps in our maps are not just frustrating, they are dangerous. Every dive into the trench is an expedition into partial knowledge, guided by data that may be inaccurate or incomplete. Explorers must be prepared for the unexpected, for terrain that does not match the charts, for features that appear suddenly in the lights of the submersible because the sonar never saw them. This uncertainty is one of the reasons why deep-sea exploration proceeds so slowly and so carefully, why each dive is planned with contingencies and backup plans, and why the total number of hours humans have spent at the bottom of the Mariana Trench can still be counted on two hands. The ocean guards its deepest secrets not with locks and walls, but with physics, using the very medium we must pass through as a barrier that distorts, absorbs, and conceals. As we continue this journey, The limitations of sonar remind us that seeing in the deep ocean is fundamentally different from seeing on land or even in space. We cannot simply point a camera or a telescope and capture what is there. We must send signals through a medium that changes them, interpret echoes that return weakened and distorted, and piece together a picture from fragments of information that are never quite complete. This is the reality of exploring the Mariana Trench, a world where even our most basic tool for understanding distance and shape struggles to function, where maps are works in progress that may never be finished, and where the seafloor itself remains stubbornly hidden behind layers of water that refuse to let sound pass through unchanged. With this challenge in mind, we now turn to an even more direct and unforgiving obstacle, one that does not just distort our measurements, but threatens to crush the very vessels we send into the abyss. The weight of the ocean is patient, immense, and absolute. With this challenge in mind, we now turn to an even more direct and unforgiving obstacle, one that does not just distort our measurements, but threatens to crush the very vessels we send into the abyss. The weight of the ocean is patient, immense, and absolute. Unlike the acoustic distortions that confuse our sonar or the darkness that limits our cameras, pressure is not a problem of information or perception. It is a physical force that acts on every square inch of every surface, pressing inward from all directions with a strength that defies ordinary comprehension. At the bottom of the Mariana Trench, this pressure reaches over 16,000 pounds per square inch, more than 1,100 times the atmospheric pressure we experience standing at sea level. To put that in terms that feel real, imagine placing a fully loaded commercial airliner, wings, engines, passengers, and all, balanced on your thumbnail. That is the force pressing against every small patch of surface area on a submersible at the deepest point of the trench. This is not a force that comes and goes, not something that builds to a peak and then releases. It is constant, surrounding, and unrelenting. From the moment a vessel begins its descent, the pressure increases steadily, adding roughly 1 atmosphere of force for every 10 meters of depth. At first, this accumulation feels gradual, almost gentle, but the mathematics are deceptive. By the time a submersible reaches 1,000 meters, it is already experiencing pressures 100 times greater than at the surface, enough to challenge the engineering of most conventional vessels. By 3,000 meters, the pressure has tripled again, and materials that seemed robust in shallower water begin to reveal their vulnerabilities. By 6,000 meters, where the Hadal zone begins, the force is so immense that only the most carefully designed and meticulously constructed vessels can survive, and even they must be constantly monitored for signs of stress. The effect of this pressure on materials is both straightforward and insidious. At the surface, metal feels solid and unyielding, a substance that holds its shape against gravity, impact, and tension. But under extreme pressure, the apparent solidity of metal becomes an illusion. Every material has a limit, a point beyond which it can no longer resist the forces acting upon it. For metals, this limit is determined by the arrangement of atoms within the crystal lattice, by the strength of the bonds holding those atoms together, and by the microscopic flaws invisible to the naked eye that are present in even the highest quality alloys. At normal pressures, these flaws are insignificant, minor imperfections that have no effect on the material's performance. But under the crushing force of the deep ocean, each tiny flaw becomes a potential point of failure, a weak spot where the metal might begin to deform, where cracks might begin to propagate, where catastrophe might begin. Engineers call this phenomenon metal fatigue, and it is one of the most serious challenges in deep-sea exploration. A sphere of titanium or high-strength steel, perfectly formed and tested at the surface, may seem flawless and invulnerable. But after a dive to the trench, that same sphere has been subjected to stresses that compress it, stretch it, and test every weld and joint. The metal does not break immediately. Instead, it accumulates damage slowly, invisibly, with each dive adding microscopic changes that are impossible to detect without sophisticated inspection. Welds, even those performed to the highest standards, contain slight variations in grain structure where the molten metal cooled and solidified. Under pressure, these variations become stress concentrators, places where the force finds a foothold. Bolts and fasteners, which hold components together, experience cyclic loading as the vessel descends and ascends, tightening and loosening ever so slightly with each change in pressure. Over time, this cycling can cause bolts to fatigue, seals to shift, and connections to weaken in ways that give no outward warning. The history of deep-sea exploration includes moments where these hidden weaknesses revealed themselves with devastating speed. There have been vessels, well-designed and carefully built, that descended into the abyss only to encounter conditions they could not withstand. In some cases, the failure was not gradual but catastrophic, an event so rapid that it completed in a fraction of a second. The physics of implosion, the inward collapse of a pressure vessel, are brutal and unforgiving. When a weak point finally gives way, the surrounding pressure does not need time to gather strength. It is already there, waiting, pressing against every surface with enormous force. The instant the hull is breached, water rushes inward at supersonic speeds, driven by the pressure differential between the interior and exterior. The collapse propagates faster than the human nervous system can react, faster than any safety system can respond. Metal walls fold inward like paper. Bulkheads crumple, and the entire structure is crushed into a fraction of its original volume in less time than it takes to blink. These catastrophic failures are rare, but they leave an indelible mark on the field of deep-sea engineering. They serve as stark reminders that the ocean at these depths does not forgive mistakes, does not offer second chances, and does not tolerate weaknesses. Every vessel that descends into the Mariana Trench carries with it the knowledge that the pressure outside is sufficient to destroy it instantly if any part of the design fails. This awareness shapes every decision, from the choice of materials to the geometry of the hull to the testing protocols that each component must pass before it is ever allowed near the water. The margin for error is not small, it is non-existent. A vessel either withstands the pressure completely or it does not survive at all. The shape of the vessel itself is one of the most important factors in determining whether it will endure. Engineers discovered long ago that certain geometries distribute pressure more evenly than others. A sphere, smooth and symmetrical, is the ideal form because it has no corners, no flat panels, no edges where stress can concentrate. Every point on the surface of a sphere is equidistant from the center, and the pressure acting on each point is balanced by the structural integrity of the material in all directions. This is why nearly every deep-diving submersible designed to reach the Hadal zone uses a spherical pressure hull. It is not an aesthetic choice, but a mathematical necessity, the closest approximation to a perfect form that human manufacturing can achieve. Yet even a sphere is not invulnerable. The perfection of the shape depends on the uniformity of the material, on the precision of the manufacturing process, and on the absence of flaws that could disrupt the even distribution of stress. Building a sphere that can withstand the pressures of the Mariana Trench requires tolerances measured in fractions of a millimeter. The thickness of the walls must be uniform, varying by no more than a tiny percentage across the entire surface. Any deviation, any spot where the metal is slightly thinner or where the crystal structure is slightly different, becomes a vulnerability. The welding process, if welds are used, must be flawless, with complete penetration and no voids or inclusions that could act as stress risers. Many modern pressure hulls are forged from a single piece of metal or machined from a solid block to avoid welds entirely, but this introduces its own challenges. The metal must be free of internal flaws, the machining must be precise, and the heat treatment must be carefully controlled to ensure that the material properties are consistent throughout. Every step of the manufacturing process is a potential source of error, and every error is a potential point of failure. Inside the sphere, the environment must remain stable, while the outside world attempts to crush it. The difference between the interior pressure, typically maintained at normal atmospheric levels for the crew or instruments, and the exterior pressure creates an enormous imbalance. At the deepest points of the trench, this difference approaches 16,000 pounds per square inch, a disparity so extreme that it puts the sphere under constant compression. The walls must be thick enough to resist this compression without buckling, yet not so thick that the vessel becomes too heavy to descend or too large to be practical. Finding this balance is one of the central challenges of pressure hull design, a problem that has no single solution, but rather a range of trade-offs between strength, weight, size, and cost. Pressure also affects how materials behave over time. A vessel that makes a single dive to the trench and returns may show no signs of damage, but a vessel that makes multiple dives accumulates stress with each descent. The metal is compressed as the pressure builds, then relaxes as the vessel ascends. This cyclic loading, repeated over many dives, causes microscopic changes in the material's structure. Dislocations in the crystal lattice move and multiply, grain boundaries shift, and the metal gradually becomes more brittle. This process, known as work hardening, can actually increase the strength of the material in some cases, but it also reduces its ductility, making it more prone to cracking under sudden loads. Engineers must track the dive history of each pressure hull, calculating the accumulated stress and determining when the vessel has reached the end of its safe operational life. This is not a matter of convenience, but of survival, because a hull that has been pushed beyond its limits may fail without warning on what seems like a routine dive. Even with the best materials, the strongest designs, and the most careful construction, the ocean at the deepest points remains a challenge that cannot be taken lightly. Every component of the submersible, from the pressure hull to the viewports to the penetrations where cables and hoses pass through the hull, must be engineered to withstand forces that are almost unimaginable. Viewports, which allow the crew to see outside, are particularly vulnerable because they interrupt the smooth, even surface of the sphere. They are typically made of thick acrylic or glass, shaped into truncated cones that are compressed inward by the pressure, actually becoming stronger as depth increases. But the interface between the viewport and the metal hull is a critical junction, a place where two different materials with different properties must work together under extreme stress. If the seal fails or the viewport cracks, the result is immediate and catastrophic. Penetrations for electrical cables, hydraulic lines, and sensor connections face similar challenges. Each one is a hole in the pressure hull, a place where the perfect symmetry of the sphere is broken. Engineers seal these penetrations with complex assemblies of gaskets, O-rings, and mechanical fittings. But every penetration is a potential weak point. The more systems the submersible carries, the more penetrations are required, and the more opportunities there are for something to go wrong. This creates a fundamental tension in deep-sea design. The desire to equip the vessel with advanced sensors, cameras, manipulator arms, and sampling equipment must be balanced against the need to minimize penetrations and maintain the integrity of the pressure hull. Every feature added to the submersible is a compromise, a trade-off between capability and safety. The materials used in pressure hull construction have evolved significantly over the decades. Early deep-sea vessels used steel, which is strong and relatively inexpensive, but also heavy. Titanium, which offers a better strength-to-weight ratio and superior resistance to corrosion in seawater, became the material of choice for many modern submersibles, though it is more expensive and more difficult to machine. Some experimental designs have explored composite materials, ceramics, and advanced alloys, each with their own advantages and limitations. But no material is perfect, and no design can eliminate risk entirely. The ocean at the bottom of the Mariana Trench is an environment that pushes every material to its limits, testing the boundaries of what human engineering can achieve. The slow, invisible accumulation of damage from repeated dives means that pressure hulls have a finite operational life. Unlike surface vessels that can be repaired and refurbished indefinitely, A deep diving submersible eventually reaches a point where the accumulated stress makes further dives too dangerous. The hull may still look flawless from the outside, with no visible cracks or deformations, but internal inspections using ultrasonic testing, X-rays, or other non-destructive methods may reveal changes in the material that signal the end of its safe service life. When that point is reached, the hull must be retired, even if the rest of the submersible is still functional. This limited lifespan adds to the cost and complexity of deep-sea exploration because it means that vessels must be periodically rebuilt or replaced, and the number of dives that can be conducted with any single hull is finite. Understanding pressure is not just a matter of engineering. It is a humbling lesson in the limits of human control. We can design vessels that resist it, we can choose materials that withstand it, and we can calculate the forces with precision, but we cannot change the fundamental physics. At the bottom of the Mariana Trench, 16,000 pounds press upon every square inch, and they will continue to press with that same relentless force, whether we are there or not. The ocean does not adapt to us. We must adapt to it, building our machines to survive in an environment that was never meant for human presence. This is the reality of pressure in the deep sea, a force so immense that it shapes every aspect of exploration. From the design of the vessels to the length of the dives to the constant awareness that every moment spent at depth is a moment spent balanced on the edge of catastrophe. As we move forward, this pressure will remain a constant companion, an invisible adversary that never rests and never relents, shaping not just the machines we build, but the very possibility of reaching the deepest places on Earth. As we move forward, this pressure will remain a constant companion, an invisible adversary that never rests and never relents, shaping not just the machines we build, but the very possibility of reaching the deepest places on Earth. Yet pressure, for all its crushing force, is not the only obstacle that transforms the trench into an alien realm. There is another barrier, equally fundamental, but operating through entirely different physics: the complete and absolute absence of light. While pressure tests the structural limits of our vessels, darkness tests the limits of our ability to perceive and document what we find. A submersible might survive the journey to the seafloor intact, its hull uncompromised and its systems functioning, but if it cannot illuminate the world around it, if its cameras cannot capture more than a few meters of visibility, then the expedition becomes a voyage through blindness, touching a world it can barely see. The journey of light into the ocean is a story of gradual extinction, a slow fade that begins the moment sunlight strikes the surface. At first, the water seems transparent, and the upper layers glow with the familiar blues and greens of shallow seas. But this transparency is deceptive. Water, even the clearest seawater far from shore, is not truly transparent at all. It is a medium that absorbs electromagnetic radiation, and it does so selectively, taking different wavelengths at different rates. The longest wavelengths, the deep reds that give blood its color and sunsets their warmth, are the first to vanish. Within 10 meters of the surface, red light has been almost entirely absorbed, drained away by water molecules that convert its energy into faint heat. Objects that appear vibrant red in air look gray or black at even modest depths, drained of the wavelengths that defined their color. Orange and yellow follow quickly, disappearing within the first few dozen meters. By 50 meters, the world has shifted toward blues and greens, the shorter wavelengths that penetrate more effectively through the density of water. Divers who descend to these depths without artificial lights describe a world that feels cold and monochromatic, where colors exist only in memory, and everything takes on the pale cast of twilight. But even these hardy wavelengths cannot survive the full journey. Green light, which seems so persistent in the upper ocean, fades as depth increases, its energy scattered by particles and absorbed by the water itself. By 200 meters, even the blues that give the ocean its characteristic hue have dimmed to almost nothing. and the world teeters on the edge of complete darkness. Below that threshold, natural sunlight becomes a memory, a phenomenon that once existed but can no longer reach this depth. The Mariana Trench lies far, far below this twilight boundary. By the time a submersible descends past 1,000 meters, it has entered a realm where sunlight has not penetrated in millions of years, where the concept of day and night has no meaning, and where any organism that has evolved in these depths has done so in perpetual darkness. This is not the darkness of a moonless night on the surface, where faint starlight still provides some reference, some sense of space and distance. This is absolute darkness, a blackness so complete that the human eye, evolved to detect even the faintest traces of light, finds nothing to see. It is a darkness that feels physical, as if the water itself has become opaque, though in reality it is simply that there are no photons left to detect, no electromagnetic radiation in the visible spectrum traveling through the medium. For the engineers designing deep-sea submersibles, this darkness presents a challenge as fundamental as pressure. If the vessel cannot see, it cannot navigate safely, cannot identify features of scientific interest, cannot document its discoveries, and cannot avoid hazards. The solution, the only solution, is to bring light with the vessel, to carry artificial illumination down into the abyss and use it to carve out a temporary bubble of visibility. Modern LED technology has made this more feasible than ever before. LEDs are efficient, converting a high percentage of electrical energy directly into light rather than heat. They are compact, allowing multiple powerful lights to be mounted on a submersible without adding excessive weight. And they are durable, capable of withstanding the vibrations, temperature changes, and mechanical stresses of deep-sea operations. Yet even the most advanced LED arrays, glowing with thousands or tens of thousands of lumens, face insurmountable physics once they descend into the trench. Light, like sound, must travel through water to be useful, and water is a hungry medium. Photons, the fundamental particles of light, are absorbed by water molecules at a rate that increases with distance. In clear, shallow water, this absorption is gradual enough that light can travel tens of meters before fading noticeably. But in the cold, dense, particle-laden water of the Hadal zone, the absorption happens much more quickly. The water is not just cold and dense, it is filled with suspended particles, microscopic fragments of organic matter, mineral grains, and the remains of organisms that have drifted down from the surface over centuries. Each particle scatters light, redirecting photons away from their intended path and spreading the beam's energy over a wider area. The result is that even the most powerful lights mounted on a submersible can only illuminate a radius of 3 to 5 meters at the bottom of the trench, sometimes less if the water is particularly turbid. Beyond that narrow circle, the darkness is absolute, an impenetrable wall that swallows every photon. This creates a profound limitation for cameras and human observers. A landscape that might stretch for kilometers in every direction is reduced to a tiny, brightly lit island surrounded by nothingness. The submersible moves through this darkness like a ship sailing at night with only a small lantern, able to see the deck beneath its feet, but blind to the ocean stretching away in all directions. Every feature, every organism, every geological formation exists in this tiny bubble of illumination for only a few moments before it passes back into darkness, possibly never to be seen again. The cameras that document these expeditions are highly sophisticated instruments, equipped with sensitive sensors capable of capturing images in low-light conditions that would leave the human eye struggling. But no amount of sensitivity can compensate for the fundamental problem. There is no light to capture beyond the narrow cone projected by the LEDs. The camera sees exactly what the lights reveal, and nothing more. In shallow water, ambient sunlight provides a background glow that softens shadows and reveals depth and distance. In the trench, there is no ambient light at all. Shadows fall sharply and absolutely, creating stark contrasts between the illuminated foreground and the black void beyond. The footage has a characteristic look, almost theatrical, as if the seafloor were a stage lit by a single spotlight with the rest of the theater lost in darkness. This narrow field of view fundamentally limits what can be discovered on any single dive. A submersible might pass within meters of a remarkable geological feature, a thriving community of organisms, or a structure that would rewrite our understanding of the trench, and never see it simply because it fell outside the small bubble of light. The pilot must make constant decisions about where to point the vehicle, where to direct the cameras, and what to investigate, knowing that every choice means dozens of other potential discoveries pass by unseen. It is an exhausting exercise in prioritization, made more difficult by the fact that the pilot often has only seconds to decide whether something glimpsed at the edge of the lights is worth a closer look or just another stretch of sediment identical to the thousands of meters already passed. The behavior of light in the trench also creates optical illusions that can deceive even experienced observers. Suspended particles, stirred up by the submersible's thrusters or drifting naturally through the water, pass through the light beams in hypnotic patterns. Each particle catches the light briefly, glowing like a tiny star before fading back into darkness. When thousands of these particles are visible at once, drifting past the camera at different speeds and distances, they create the illusion of motion even when the submersible is stationary. The brain, trained to interpret movement in the visual field as an indication that the observer is moving, can be fooled into thinking the vessel is traveling forward or backward when in reality it is simply the particles flowing past. This effect is remarkably similar to what astronauts report when ice crystals or debris float past their spacecraft, creating the sensation of motion in the vacuum of space. These illusions are not just curiosities, they affect navigation and situational awareness. A pilot who believes the submersible is moving forward based on visual cues might actually be drifting sideways or even backward due to currents. The only way to maintain accurate awareness of position and motion is to rely on instruments, gyroscopes, accelerometers, sonar, and positioning systems that track the vessel's location relative to known reference points. But these instruments provide abstract information, numbers, and graphs rather than the intuitive sense of space that vision normally offers. Learning to trust instruments over visual perception is one of the most challenging aspects of piloting in the deep sea, a skill that must be developed through training and experience because the instincts that serve us well on the surface become liabilities in the darkness of the trench. The density and coldness of the water at depth also affect the lights themselves. Cold temperatures reduce the efficiency of LEDs, causing them to produce less light for the same amount of electrical power. The difference is not dramatic, but in an environment where every lumen counts and power is strictly limited, even a 10 or 15% reduction in light output is significant. The cold also affects the materials used in the light housings and electrical connections. Seals and gaskets must remain flexible and watertight, but extreme cold can cause some materials to stiffen, increasing the risk of leaks. Engineers compensate by carefully selecting materials and by designing thermal management systems that keep critical components within acceptable temperature ranges. But this adds complexity and consumes power that might otherwise be used for illumination or other functions. The scattering of light by particles creates another phenomenon that photographers and videographers in the trench must constantly battle: backscatter. When light from the LEDs hits a particle close to the camera lens, it reflects directly back toward the camera, creating a bright spot in the image that obscures whatever lies behind it. With thousands or millions of particles suspended in the water, the effect can be overwhelming, turning the footage into a blizzard of white specks that make it difficult to see the seafloor or any organisms in the scene. This is why most deep-sea cameras use lights mounted away from the camera itself, positioned at angles that minimize backscatter by ensuring that reflected light does not travel directly back into the lens. But this technique has limits, and in particularly turbid water, backscatter remains an unavoidable problem that degrades image quality. The combination of limited light penetration, Particle scattering and the absence of ambient illumination means that creating a comprehensive visual record of the trench is extraordinarily difficult. Each dive produces hours of footage, but that footage captures only a tiny fraction of the environment, a narrow path through the darkness that reveals isolated glimpses rather than a coherent picture. It is as if one were trying to understand a vast library by walking through it with a flashlight, able to read a few book spines here and there, but never able to see the full collection or understand how the pieces fit together. The footage is valuable, scientifically important, and often stunning in its revelation of strange life forms and alien landscapes, but it is also frustratingly incomplete. Recent developments in imaging technology offer some potential for improvement. Advances in low-light sensors, better algorithms for image processing, and more efficient LED designs are gradually pushing the boundaries of what can be captured in the deep ocean. Some experimental systems use structured light, projecting patterns onto the seafloor that can be analyzed to create three-dimensional models, even in limited visibility. Others use multiple cameras and lights positioned at different angles to reduce shadows and improve depth perception. But all of these techniques still depend on the fundamental constraint that light must travel through water, and no technology can change the physics of absorption and scattering. The trench will always be a dark place, and any artificial light brought into it will always create only a small, temporary island of visibility. This limitation shapes not just how we see the trench, but how we think about it. The darkness enforces a kind of intimacy, forcing attention onto small details, individual organisms, and close-up textures rather than broad vistas. It makes every discovery feel immediate and personal, as if the submersible and its occupants are the only witnesses to these hidden corners of the planet. But it also means that our understanding of the trench as a whole remains fragmentary, built from thousands of these small, intimate observations that must somehow be assembled into a coherent picture. The darkness is not just an obstacle to overcome. It is a defining characteristic of the environment, shaping the lives of the organisms that live there and the methods we must use to study them. As we continue deeper into the story of the trench, this darkness will remain ever present, a reminder that some places on Earth are not meant to be fully seen, only glimpsed in fleeting moments of borrowed light before they retreat once more into the eternal black. As we continue deeper into the story of the trench, this darkness will remain ever present, a reminder that some places on Earth are not meant to be fully seen, only glimpsed in fleeting moments of borrowed light before they retreat once more into the eternal black. But the absence of light is only part of the transformation that occurs as a submersible descends into the abyss. The water itself changes character, becoming something fundamentally different from the familiar liquid we know at the surface. This transformation is not visible, not something that cameras can capture or lights can reveal, but it affects every aspect of a dive, from the behavior of the vessel to the performance of its systems, to the energy required to complete the mission. The cold and chemistry of the deep ocean create an environment that is not just dark and pressurized, but also dense, viscous, and hostile to the machines we send into it. The change begins in earnest at the thermocline, an invisible boundary layer where the ocean's temperature drops rapidly over a relatively short vertical distance. Near the surface, sunlight warms the water, creating a mixed layer where temperatures remain relatively constant, often 15 to 20 degrees Celsius or warmer depending on location and season. This warm layer can extend down 100 meters or more, stirred by waves and currents that distribute heat evenly. But below this comfortable zone, the warmth ends abruptly. The thermocline marks the transition between the sun-warmed surface and the cold, stable waters of the deep. Within a span of 50 to 100 meters, temperatures can plunge by 10 or even 15 degrees, a gradient so sharp that it creates a density barrier as distinct as a physical wall. For a descending submersible, crossing the thermocline is a moment of transition that affects multiple systems simultaneously. The hull, which has been cooling gradually during the descent, suddenly encounters water that is significantly colder, causing the metal to contract more rapidly. This contraction is small, measured in fractions of a millimeter, but in a precision-engineered pressure vessel where tolerances are tight, even small changes matter. Seals that were seated perfectly in warmer water may shift slightly as the metal around them shrinks. Joints and connections experience thermal stress as different materials contract at different rates. The submersible does not fail at this boundary, but it enters a new regime where everything behaves differently, where the comfortable predictability of surface conditions gives way to the strange physics of the deep. Below the thermocline, the cold deepens relentlessly. By the time a vessel reaches 3,000 or 4,000 meters, the water temperature has dropped to just a few degrees above freezing, typically between 1 and 4 degrees Celsius. This is not the crisp, invigorating cold of a winter morning, but a profound, bone-deep chill that permeates everything. At these temperatures, water becomes denser, its molecules packing more tightly together as thermal motion slows. This increased density has immediate consequences for buoyancy, the fundamental principle that allows submersibles to descend and ascend. A vessel that was neutrally buoyant at the surface, perfectly balanced so that it neither sinks nor floats, will find itself behaving differently in the denser water below the thermocline. The same volume of water displaced by the hull now weighs more, providing greater upward force, but the vessel itself also becomes denser as its materials cool and contract. The net effect depends on the specific design of the submersible and the materials used in its construction. Some vessels become slightly more buoyant as they cool, requiring the release of ballast or the use of downward thrusters to maintain depth. Others become less buoyant, sinking more readily and requiring careful management to avoid an uncontrolled descent. But the challenge is not just the overall change in buoyancy, it is the unpredictability of that change. The water at depth is not uniform. It is stratified into layers with different temperatures and salinities, each layer having its own distinct density. As a submersible moves through these layers, its buoyancy shifts subtly and constantly, requiring continuous adjustments that consume power and attention. A pilot cannot simply set a depth and forget it. Maintaining position in the water column is an active task that demands constant vigilance. The chemistry of the deep water adds another dimension to this complexity. The Mariana Trench is filled not just with cold water, but with cold brine, seawater that is slightly saltier than the global average. This brine is ancient, water that has spent decades or even centuries circulating through the deepest parts of the Pacific, accumulating dissolved minerals and salts as it travels. The slow currents that fill the trench carry this water from distant regions, sometimes from thousands of kilometers away, and it settles into the lowest points because it is denser and heavier than the water above. The difference in salinity may be only a few parts per thousand, but this is enough to increase the water's density by several percent, creating a distinct layer that behaves almost like a separate fluid. This dense brine has properties that affect everything from sonar performance to the thermal environment surrounding the submersible. It is colder than the water above it, often by a degree or more, adding to the challenge of thermal management. It is also more viscous, resisting motion more strongly and requiring more energy from thrusters to maintain speed or change direction. When a submersible enters a layer of cold brine, it is as if the ocean has become thicker, less willing to let the vessel pass through easily. The thrusters must work harder, spinning faster and consuming more power to achieve the same thrust. This increased power consumption accelerates the drain on batteries, shortening the time available for exploration and forcing pilots to make difficult choices about how to allocate their limited energy reserves. The cold itself is perhaps the most insidious challenge because it affects so many systems simultaneously. Batteries, which store electrical energy in chemical form, rely on reactions that occur between electrodes and electrolytes. These reactions are temperature-dependent, proceeding more quickly when warm and more slowly when cold. At the temperatures found at the bottom of the Mariana Trench, battery performance can drop by 30 to 50% compared to surface conditions. A battery bank that might provide 8 hours of operation in warm water may deliver only 4 or 5 hours in the deep, and the voltage it supplies may be less stable, fluctuating as the chemical reactions struggle to keep pace with demand. This reduction in performance is not a flaw in the batteries. It is a fundamental consequence of thermodynamics, the same physics that makes car batteries sluggish on cold winter mornings, but magnified by the extreme conditions of the deep ocean. To combat this problem, engineers designed submersibles with thermal management systems that attempt to keep critical components warm. Batteries may be insulated, surrounded by materials that slow the transfer of heat from the warm interior to the cold water outside. Some designs include active heating elements, small resistive heaters that warm the battery compartment using a portion of the stored energy. This creates a paradox. Energy must be spent to keep the batteries warm enough to deliver their full capacity, but spending that energy reduces the total available for other tasks. The optimization becomes a delicate balance, determining exactly how much heating is necessary to maintain acceptable performance without wasting so much power that the net benefit is lost. The Fendouje submersible, which conducted the MEER expeditions and set records for sample collection, incorporates sophisticated thermal management that allows it to operate at the seafloor for up to 6 hours, a significant improvement over earlier designs that struggled to maintain systems in the extreme cold. Electronics, too, suffer in the cold. Semiconductors, the building blocks of modern computers and control systems, change their electrical properties as temperature drops. Transistors may switch more slowly, signals may degrade, and timing circuits may drift out of specification. While these effects are generally well understood and can be compensated for in design, they add complexity and require that every electronic component be tested and rated for operation at low temperatures. Sensors that measure pressure, temperature, salinity, or other environmental parameters may become less accurate or less responsive in the cold, introducing errors that must be accounted for in data analysis. Cameras and lights, as we have already seen, also lose efficiency, producing less output for the same power input and forcing trade-offs between illumination and endurance. Mechanical systems face their own cold-related challenges. Lubricants, the oils and greases that reduce friction in moving parts, become more viscous as temperature drops. A lubricant that flows smoothly at room temperature may thicken into a stiff paste at 4 degrees Celsius, increasing friction and making motors and actuators work harder. In extreme cases, lubricants can become so viscous that they prevent mechanisms from moving at all, freezing joints and gears until they warm up again. Engineers select lubricants specifically for their low-temperature performance, choosing formulations that remain fluid even in the coldest conditions, but this is another area where compromises must be made. Lubricants that perform well in cold may not provide optimal protection against wear at higher temperatures, and submersibles that operate across a wide range of depths must use lubricants that are adequate at all conditions rather than optimal at any one. Seals and gaskets, which prevent water from entering pressure housings and flooding sensitive equipment, are also affected by cold. Rubber and elastomeric materials lose flexibility as they cool, becoming stiffer and less able to conform to irregular surfaces. A seal that provided a perfect watertight barrier at the surface may develop microscopic leaks at depth as the cold reduces its ability to compress and fill gaps. This is why deep-sea equipment uses specialized seal materials, often fluoropolymers or other compounds engineered to maintain their properties across a wide temperature range. Even with these materials, seals are a constant concern, inspected before every dive and replaced regularly because the consequences of failure are so severe. The combination of cold and pressure creates conditions that are difficult to replicate in laboratory testing. A pressure chamber on the surface can simulate the crushing forces of the deep, and a cold room can replicate the low temperatures, but combining both simultaneously while also accounting for the chemical composition of seawater and the duration of exposure is technically challenging and expensive. This means that many components of deep-sea submersibles are tested separately under pressure or cold, but not under the exact conditions they will experience during an actual dive. Engineers must extrapolate from test data, using models and calculations to predict how systems will behave when multiple stresses are combined. This introduces uncertainty, and it is one reason why new submersible designs proceed cautiously, often conducting shallow test dives before attempting to reach maximum depth. The density variations in the water also create challenges for navigation and stability. A submersible descending through layers of different density may experience sudden changes in buoyancy that cause it to accelerate unexpectedly or to lurch slightly as it crosses a boundary. These transitions are usually gentle, but in a confined space near the seafloor or close to the trench walls, even a small, uncontrolled movement can be dangerous. Pilots learn to recognize the signs of approaching a density boundary, watching for changes in temperature or salinity readings, and adjusting ballast or thrust preemptively to maintain smooth control. But not all boundaries are detected in advance, and encountering an unexpected pocket of denser or lighter water requires quick reaction to prevent the submersible from drifting into a hazard. The coldness of the water also affects the thermal environment inside the pressure sphere. Even with insulation, the chill of the surrounding ocean gradually penetrates inward, cooling the interior and making conditions uncomfortable for any crew aboard. Submersibles designed for human occupancy must include heating systems to maintain a livable temperature inside the sphere, but this heating consumes power that competes with propulsion, lighting, and scientific instruments. On long dives, the crew may need to tolerate cooler interior temperatures to conserve energy, bundling in layers of clothing and accepting discomfort as a necessary trade-off for extended bottom time. For uncrewed vehicles, interior temperature is less of a concern, but the electronics still require thermal management to prevent failures. The interplay between cold, chemistry, and pressure creates an environment that is hostile not just to human life, but to machines as well. Every system aboard a submersible is operating at the edge of its performance envelope, struggling against conditions that drain energy, reduce efficiency, and introduce uncertainties. The water is not just a medium to move through. It is an active participant in the dive, a presence that squeezes, chills, and tests every component. Understanding this environment and designing systems that can function within it requires not just engineering skill, but also humility and acceptance that the ocean sets the rules and that our machines must adapt or fail. The trench does not yield easily to exploration because it is not a passive void, but a dynamic, complex environment where the physics and chemistry of water at extreme conditions create barriers that cannot be ignored or overcome through brute force alone. As we move forward in this journey, the cold and chemistry of the trench will continue to shape every aspect of exploration. They affect how long a dive can last, how much data can be collected, how accurately instruments can measure, and how safely the submersible can operate. They are invisible challenges, not as dramatic as crushing pressure or absolute darkness, but just as fundamental and just as limiting. Together, these factors create an environment where energy is precious, time is limited, and every decision must be made with the knowledge that the ocean is not a forgiving place. The next challenge we will explore builds on this foundation, examining how the trench's geological restlessness adds yet another layer of unpredictability to an already formidable environment. Together, these factors create an environment where energy is precious, time is limited, and every decision must be made with the knowledge that the ocean is not a forgiving place. The next challenge we will explore builds on this foundation, examining how the trench's geological restlessness adds yet another layer of unpredictability to an already formidable environment. While pressure crushes, cold drains, and darkness conceals, there is another characteristic of the Mariana Trench that makes exploration so difficult. It never stops moving. This is not the obvious motion of currents or the drifting of water masses, but something deeper and more fundamental. The trench sits atop one of the most geologically active zones on Earth, a place where tectonic plates grind against each other in slow-motion collision. And this activity manifests in ways that turn the seafloor into an unstable, shifting landscape that refuses to be mapped with certainty or navigated with complete confidence. The Pacific Plate descends beneath the Philippine Plate at a rate of 5 to 10 centimeters per year, a pace so gradual that it would be invisible to any observer watching in real time. But this motion is not smooth. The plates do not slide past each other like polished surfaces gliding on oil. They catch and stick, building up stress over years or decades, and then release that stress suddenly in earthquakes. At the surface, far from the subduction zone, these earthquakes might be felt as gentle tremors or not noticed at all. But within the trench itself, at the very boundary where the plates meet, the seismic activity is constant and intense. Micro-earthquakes, too small to register on most seismographs designed for monitoring surface events, ripple through the rock and sediment hundreds or even thousands of times per year. Each one is a small adjustment, a moment when accumulated stress finds release, and together they form a continuous background of geological noise that shapes the environment in profound ways. These micro-earthquakes are not dangerous in the way that a major seismic event can be. They do not generate tsunamis or collapse buildings. Their magnitude is typically so low that instruments must be placed directly on the seafloor to detect them reliably. But for a submersible operating near the bottom of the trench, these tremors create hazards that are both immediate and lasting. The most direct effect is on the sediment. The trench floor is covered with layers of soft material that has accumulated over millions of years. A mixture of organic remains, mineral particles, and volcanic ash that forms a blanket, sometimes tens or even hundreds of meters thick. This sediment is not consolidated into solid rock. It is loose, waterlogged, and held in place primarily by its own weight and the friction between particles. When a micro-earthquake shakes the seafloor, even gently, it disrupts this delicate stability. The shaking causes particles to lose contact with their neighbors, and what was solid becomes temporarily fluid, a process called liquefaction. Sediment that was resting on a slope begins to flow downward, moving like thick syrup under the pull of gravity. On the steep walls of the trench, where gradients can exceed 30 or 40 degrees, this movement can accelerate into an underwater landslide, a cascade of material that tumbles down the slope, gathering speed and volume as it descends. These landslides are not the dramatic, fast-moving avalanches we see in mountain terrain. They move more slowly, sometimes only meters per second, but they carry enormous mass. Thousands or even millions of tons of sediment can be mobilized by a single event, and anything in the path of this flow, whether a piece of scientific equipment, a sensor array, or even a submersible that has landed in the wrong place at the wrong time, can be buried in minutes. Even when the sediment does not flow as a coherent landslide, the shaking stirs it into suspension, creating clouds of particles that hang in the water column like dense fog. These clouds can persist for hours or even days after the initial tremor, drifting with slow currents and settling gradually back to the seafloor. For a submersible trying to navigate or conduct observations during this time, the suspended sediment creates a visibility crisis far worse than the normal limitations imposed by darkness and limited light. The lights that would normally illuminate a few meters of clear water now reveal only a thick, swirling soup of particles. Cameras become useless, capturing nothing but a murky haze. Sonar, already challenged by the complex acoustic environment of the trench, becomes even less reliable as the suspended sediment scatters and absorbs sound pulses. The submersible is effectively blind, unable to see where it is going or what lies ahead, forced to rely entirely on instruments and memory of the terrain as it existed before the tremor. This problem is not occasional or rare. The micro-earthquake activity in the Mariana Trench is so frequent that encountering disturbed sediment during a dive is not an unlikely event, but a realistic possibility that must be planned for. Pilots train for operations in zero visibility, learning to navigate using only sonar returns and inertial guidance systems. But this training cannot eliminate the danger entirely. A cloud of suspended sediment might hide a rock outcrop, a steep drop-off, or a piece of equipment left from a previous expedition. Moving blindly through such an environment is inherently risky, and it is one reason why dives into the trench proceed with such caution, why descent and ascent rates are kept slow, and why missions often include long periods of simply hovering and waiting for conditions to improve before proceeding with planned activities. The instability of the seafloor also means that maps of the trench become outdated more quickly than maps of more stable regions. A sonar survey conducted one year might show a particular feature, a ridge or a depression, in a specific location. But if a landslide occurs between that survey and a subsequent dive, the feature may have been buried, altered, or displaced. The map that the submersible crew is relying on no longer accurately represents reality, and what they encounter when they reach the seafloor may be substantially different from what they expected. This uncertainty adds another dimension to the challenge of exploration. Not only is the initial mapping incomplete and imprecise due to acoustic limitations, but even the data that has been collected cannot be fully trusted because the environment itself is dynamic. The trench is not a static museum piece preserved unchanged for study. It is a living geological system that constantly rearranges itself. The MEER project, with its comprehensive sampling across multiple depths and locations, provided new evidence of just how heterogeneous and variable the trench environment is. The data collected between 2021 and 2025 revealed that conditions at the seafloor can vary dramatically over short distances. Adjacent sampling sites, separated by only a few hundred meters, sometimes showed completely different sediment compositions, microbial communities, and chemical profiles. Part of this variation is due to the influence of local geology, the presence or absence of fluid seeps, and differences in sediment accumulation rates. But part of it is also due to the episodic nature of sediment disturbance. A site that was recently affected by a landslide might be covered with fresh material from higher up the slope, while a nearby site that escaped disturbance retains older, more stable sediment layers. This patchwork of conditions makes it difficult to generalize findings from one location to another and underscores the need for extensive, repeated sampling to build a comprehensive understanding. The microearthquakes also affect the operation of any long-term monitoring equipment that scientists might wish to deploy in the trench. Sensors and instruments left on the seafloor must be designed not only to withstand pressure and cold, but also to survive being shaken, potentially buried by sediment, or even knocked over and displaced by flows. Recovery of these instruments after a deployment period of months or years is never guaranteed. Some are never found again, presumably buried under new sediment or swept away by underwater currents and landslides. Each lost instrument represents not just a financial cost, but also a gap in the data record, months of measurements that might have revealed important patterns or events, but are now simply absent. This risk makes long-term monitoring in the trench expensive and frustrating, requiring redundancy and careful site selection to maximize the chances that at least some instruments will survive and be recoverable. The geological restlessness of the trench also creates opportunities, however. The same processes that make exploration difficult also expose fresh rock and sediment from deeper layers, bringing to the surface materials that would otherwise remain buried and inaccessible. Landslides can reveal cross-sections through sediment layers, like the pages of a book opened suddenly, allowing scientists to study the history of deposition and environmental change. Fluid seeps, which are often associated with faults and fractures created by seismic activity, provide windows into the subsurface environment and support the chemosynthetic ecosystems that thrive in the darkness. The instability is not just a hazard, but also a driver of the trench's remarkable biodiversity and geological complexity. Understanding this duality, recognizing that the same forces that threaten exploration also create the phenomena that make the trench scientifically fascinating, is essential for anyone attempting to study this environment. The sediment itself, when it is not being stirred into suspension, records the history of seismic activity in its layering. Geologists who analyze cores taken from the trench floor can identify turbidite deposits, layers of sediment that were rapidly emplaced by underwater flows triggered by earthquakes. These layers are distinct from the normal, slowly accumulated background sediment and they provide a timeline of past events stretching back thousands or even millions of years. By studying these records, scientists can reconstruct the frequency and intensity of seismic activity in the trench over geological timescales, gaining insights into the long-term behavior of the subduction zone. But collecting these cores requires that the submersible or sampling device remain stable on the seafloor long enough to drill or push a tube into the sediment, extract it, and seal it for return to the surface. In an environment where the ground might shake without warning and where currents can stir up obscuring clouds of particles, this is a delicate and challenging operation. The unpredictability of the trench's geological activity means that no two dives are exactly alike. A crew that descended to a particular location and found it calm and clear might return weeks or months later and find it turbid and disturbed. A sampling site that yielded excellent results on one expedition might be inaccessible on the next due to fresh sediment accumulation or changes in seafloor topography. This variability demands flexibility in mission planning and an acceptance that not all objectives can be achieved on every dive. Scientific teams must prioritize their goals, identify primary targets and backup options, and remain ready to adapt their plans in real time based on what they encounter. The trench does not accommodate rigid schedules or fixed itineraries. It demands a more improvisational approach, guided by expertise and experience, but always open to the unexpected. The combination of micro-earthquake activity, unstable sediment, and the resulting variability in seafloor conditions adds yet another layer of challenge to the already formidable task of exploring the Mariana Trench. It is not enough to build a submersible that can withstand pressure, generate light in darkness, and operate in extreme cold. The vessel must also be able to navigate an environment that shifts and changes, where the seafloor of today may not match the map of yesterday, and where visibility can vanish without warning as sediment boils up into the water. These challenges cannot be solved through engineering alone. They require careful planning, conservative decision-making, and a willingness to accept that some aspects of the trench will always remain unpredictable. The geological restlessness that makes the trench so difficult to explore is also a reminder that we are visitors in a world shaped by forces far older and more powerful than human technology. Forces that will continue their work long after our brief explorations have ended and our machines have returned to the surface. The geological restlessness that makes the trench so difficult to explore is also a reminder that we are visitors in a world shaped by forces far older and more powerful than human technology, forces that will continue their work long after our brief explorations have ended and our machines have returned to the surface. Yet even if the seafloor were perfectly stable, even if the sediment never stirred and the maps never changed, there would still remain one fundamental barrier that limits every dive into the Mariana Trench more severely than any other: energy. All the engineering brilliance that goes into pressure hulls, all the sophisticated sensors and cameras, all the careful planning and training ultimately become irrelevant if the submersible runs out of power. Energy is the silent enemy, the invisible constraint that shapes every decision and limits every ambition, turning what could be extended scientific expeditions into brief, carefully rationed visits that must end long before all questions are answered. The problem begins with a simple but unforgiving equation. A submersible descending into the trench must carry all its energy with it in the form of batteries. There are no power lines stretching down from the surface, no way to refuel or recharge at depth, and no external energy sources that can be tapped once the dive begins. Whatever electrical energy is stored in the battery banks when the vessel leaves the surface is all it will have for the entire mission. The descent that takes hours, the time spent working on the seafloor, and the equally long ascent back to safety. Every system aboard the submersible, from life support and communications to lights and thrusters to scientific instruments, draws from this finite reservoir. The energy budget for a dive is not merely tight, it is ruthlessly constraining, forcing trade-offs at every moment between competing needs and creating situations where difficult choices must be made about what to power and what to leave dark. We have already seen how the cold of the deep ocean reduces battery performance by 30 to 50% compared to surface conditions. This is not a minor inconvenience, but a catastrophic degradation that transforms the energy equation. A battery bank designed to provide 8 hours of operation at room temperature might deliver only 4 hours at the temperatures found at the bottom of the trench, and those 4 hours must cover far more than just the working time on the seafloor. The descent itself consumes power as the submersible's thrusters fight against its own buoyancy, adjusting trim and maintaining course through layers of water with different densities. The ascent, though assisted by dropping ballast weights, still requires thruster activity to control the rate of rise and ensure the vessel surfaces in the correct location. By the time all phases of the dive are accounted for, the actual time available for exploration, for filming, for sampling, and for the scientific work that justifies the entire expedition may be only a fraction of the theoretical battery life. Thrusters are among the most power-hungry systems on any submersible. These devices, typically electric motors driving propellers or impellers, must push the vessel through water that becomes denser and more viscous with depth. At the bottom of the trench, moving the same distance at the same speed requires nearly twice as much energy as it would in the warmer, less dense water near the surface. Every adjustment in position, every movement to investigate a feature or collect a sample. Every correction to counteract an unexpected current drains the batteries at an accelerated rate. Pilots learn to minimize thruster use, to plan movements carefully, and to take advantage of the vessel's momentum rather than fighting against it, but there is a limit to how much can be conserved. A submersible that remains motionless to save power accomplishes nothing. It must move to explore, and movement requires energy that cannot be recovered. Lighting presents another cruel dilemma. As we have seen, the darkness at depth is absolute, and artificial lights are essential for cameras to capture any imagery at all. But powerful LED arrays, even with their superior efficiency compared to older lighting technologies, consume substantial power, especially when operated at the intensities needed to illuminate through the particle-laden, light-absorbing water of the Hadal zone. A submersible might carry lights capable of producing tens of thousands of lumens, but running them continuously would drain the batteries in a matter of hours. Instead, lights must be used strategically, powered on only when actively filming or photographing, then switched off during transits or when simply monitoring instruments. This creates gaps in the visual record, moments when something potentially significant might pass by unseen because the lights were off to conserve energy. Every decision to illuminate is a small bet that what will be seen is worth the cost in battery life. Cameras and scientific sensors, though individually less power-hungry than thrusters or lights, add up when combined. High-resolution video cameras, temperature and salinity probes, sonar systems for close-range navigation, manipulator arms for collecting samples, and communication equipment all draw power continuously or in bursts. Each instrument represents a capability, a way of learning something new about the trench, but also a drain on the limited energy supply. Mission planners must decide in advance which instruments are essential and which can be left powered down or removed entirely to extend the dive time. These decisions are never easy because every instrument was included for a reason. Every sensor has a specific scientific purpose, and leaving any of them inactive means accepting that certain questions will go unanswered. Thermal management, already discussed in the context of keeping batteries and electronics warm enough to function, is itself a major energy consumer. Heaters that maintain acceptable operating temperatures for critical systems must run almost continuously during deep dives, drawing power that could otherwise be used for propulsion or science. The paradox is cruel. Energy must be spent to prevent the cold from degrading the systems that store and deliver energy. The efficiency of this heating varies with design, insulation quality, and the temperature differential between the interior and exterior, but it is never free. Some submersibles dedicate 20 to 30% of their total energy budget simply to thermal management, a tax paid to the environment that reduces the power available for everything else. Given these constraints, it might seem logical to consider alternative power sources. Nuclear power, for instance, has been used successfully in submarines for decades, providing virtually unlimited energy for propulsion and systems during extended missions. A nuclear reactor does not depend on batteries that degrade in the cold. It generates heat continuously through controlled fission reactions, and that heat can be converted to electricity through turbines or thermoelectric generators. Yet despite these advantages, nuclear power is not used in deep-sea submersibles, and the reasons reveal much about the unique challenges of Hadal exploration. First, nuclear reactors are heavy and large, requiring substantial shielding to protect occupants and equipment from radiation. The weight alone would make it difficult to achieve the neutral buoyancy needed for a submersible to descend and ascend controllably. The size would conflict with the need to keep the pressure hull as small and spherical as possible to withstand the crushing forces at depth. Second, nuclear reactors generate heat that must be dissipated to prevent overheating and damage to reactor components. On surface submarines, this heat is dumped into the surrounding seawater through heat exchangers, a process that works well because there is always a temperature gradient between the hot reactor coolant and the relatively cool ocean. But at the bottom of the Mariana Trench, the water is already near freezing, and while this might seem ideal for cooling, the extreme cold creates its own problems. Systems designed to operate with a moderate temperature difference might fail when exposed to water only a few degrees above zero. Components that were warm might crack or distort when suddenly cooled. Managing the thermal environment of a nuclear-powered submersible in the deep ocean would require complex engineering that adds more weight, more complexity, and more potential failure points. Third, and perhaps most importantly, the environmental and safety risks of deploying nuclear reactors in the deep ocean are considered unacceptable by most regulatory bodies and scientific organizations. The Mariana Trench is not a controlled laboratory, but a remote, poorly understood ecosystem. The possibility, however remote, of a reactor breach, a radiation leak, or a failure that leaves radioactive material on the seafloor is a risk that the scientific community and international maritime authorities have deemed too great. The deep ocean is already contaminated in some areas by Cold War-era dumping of nuclear waste, and there is no appetite for adding new sources of potential contamination, especially in the name of exploration. The political, ethical, and environmental considerations overwhelm the technical advantages, leaving chemical batteries as the only realistic option despite their severe limitations. The result is that every deep dive into the trench becomes an exercise in energy rationing, a mission planned with the precision and caution of a spacecraft, operating far from any possibility of rescue or resupply. Controllers and pilots must track power consumption in real time, monitoring battery voltage and current draw, comparing actual usage against predicted models, and making continuous decisions about how to allocate the remaining energy. If a thruster draws more power than expected, perhaps because of increased water density or a mechanical issue, then time must be cut from another activity. If lighting requires longer periods of operation to capture critical imagery, then the transit to the next sampling location might need to be slower, or the visit to a secondary site might need to be canceled entirely. These adjustments happen throughout the dive, each one a small compromise that shapes what can be accomplished and what must be deferred to a future expedition. The Fendouje submersible, with its 6-hour operational capability at the seafloor, represents a significant achievement in energy management. This endurance allows the crew to conduct meaningful scientific work without the constant pressure of an immediate return, but even 6 hours is a brief window when the tasks include navigating to specific locations, deploying and recovering instruments, collecting multiple samples from different sites, documenting findings with cameras, and ensuring safe margins for ascent. The engineers who designed Fendouje optimized every system for efficiency, selected battery chemistries that maintain performance in cold conditions, and incorporated thermal management that minimizes power consumption while still protecting critical components. Yet despite these advances, the vessel still operates under tight energy constraints that limit how much can be achieved on any single dive. The energy challenge evokes comparisons to some of the most dramatic moments in space exploration. The Apollo 13 mission, where astronauts and ground controllers worked desperately to stretch limited power and life support after an oxygen tank explosion is often cited as an example of human ingenuity under extreme constraint. The astronauts had to power down nearly every system, huddle in the cold as the spacecraft drifted through space, and make agonizing decisions about what could be kept running and what had to be shut off to ensure there would be enough power to get home. A submersible at the bottom of the Mariana Trench operates under similar pressures, though the scenario is planned rather than accidental. Every dive is, in a sense, a controlled Apollo 13 scenario, where the crew accepts from the start that they have limited resources and must use them with absolute discipline, knowing that running out of power 11 kilometers below the surface is not an inconvenience, but a potential catastrophe. The analogy is imperfect, but instructive. Spacecraft can coast through the vacuum of space without using power, relying on momentum and gravity to carry them along their trajectories. A submersible in the ocean has no such luxury. It is constantly fighting against gravity, buoyancy, currents, and drag, all of which require energy to manage. There is no coasting, no free ride, only continuous expenditure of power to maintain control and position. This makes the energy challenge even more acute than in space exploration, where at least some phases of a mission can proceed without propulsion. In the trench, stopping all power consumption means surrendering control, allowing the vessel to drift wherever currents take it, and hoping that it does not collide with the seafloor or a wall before power can be restored. Engineers continue to search for ways to extend dive times and improve energy efficiency. Advances in battery technology, particularly in lithium-based chemistries that maintain better performance at low temperatures, offer incremental improvements. More efficient motors and thrusters, optimized propeller designs, and lighter materials that reduce the overall mass of the submersible all contribute to reducing energy consumption. Software that manages power distribution intelligently, shutting down non-essential systems automatically, and optimizing thruster use based on real-time conditions adds another layer of efficiency. But all of these advances, while valuable, cannot change the fundamental physics. Batteries have finite energy density, cold reduces their performance, and moving a massive object through viscous fluid requires work that must be powered by something. The improvements buy more time, extend capabilities slightly, and reduce risk, but they do not eliminate the energy constraint that ultimately determines how long any submersible can remain in the abyss. This constraint shapes not just individual dives, but the entire strategy of deep ocean exploration. Because each dive is so limited in duration and so expensive in terms of ship time, crew effort, and equipment wear, every mission must be planned to maximize scientific return within the available energy budget. This leads to a focus on specific, well-defined objectives rather than open-ended exploration. A dive might target a particular geological feature identified in sonar data, a specific depth range for biological sampling, or a location where previous expeditions reported unusual phenomena. The days of simply descending and wandering to see what might be found are largely over, replaced by carefully choreographed missions where every minute is accounted for and every action serves a predetermined purpose. This approach is scientifically efficient, but also limiting, because it reduces the opportunity for serendipitous discoveries, for stumbling upon something unexpected that changes our understanding in ways that no amount of planning could anticipate. The energy budget, silent and invisible but utterly inflexible, ensures that the trench remains a place of brief visits and incomplete surveys, a frontier that yields its secrets slowly and reluctantly, one carefully rationed dive at a time. The energy budget, silent and invisible but utterly inflexible, ensures that the trench remains a place of brief visits and incomplete surveys, a frontier that yields its secrets slowly and reluctantly, one carefully rationed dive at a time. Yet even if unlimited energy were somehow available, even if batteries could operate indefinitely in the cold and power every system without constraint, another fundamental barrier would still limit what can be achieved in the Mariana Trench. Communication. The same water that crushes, chills, and conceals also isolates, cutting off the submersible from the surface world almost completely. The electromagnetic waves that carry our voices, our data, and our commands through air with effortless speed simply cannot penetrate seawater. Radio signals, which connect spacecraft across millions of kilometers of vacuum, die within meters of entering the ocean, absorbed by the conductive salt water that acts as an impenetrable shield. At the bottom of the trench, a submersible is more isolated than a probe on Mars, unable to send or receive messages except through methods that are slow, limited, and unreliable. The physics of electromagnetic propagation through seawater are unforgiving. Radio waves are attenuated exponentially with distance, their energy absorbed by water molecules and converted into heat at a rate that depends on frequency. Higher frequencies, which could carry more data, are absorbed even more quickly than lower frequencies. At the frequencies typically used for communication, a radio signal that could reach around the world through air or space can barely penetrate a few meters of seawater before becoming too weak to detect. This is not a problem that can be solved with more power. Increasing transmitter strength extends the range slightly, but the exponential nature of the attenuation means that even enormous power levels achieve only modest improvements. A transmitter that could broadcast across an ocean at the surface might reach only 10 or 20 meters at depth before its signal vanishes into noise. This leaves acoustic communication, sound waves, as the only practical method of sending information between a submersible and the surface. But acoustic communication in the ocean, and particularly in the extreme environment of the Mariana Trench, is nothing like the crisp, reliable radio links we take for granted. Sound travels through water at roughly 1,500 meters per second, about 4.5 times faster than through air. But over a distance of 11 kilometers, even this speed creates significant delays. A command sent from the surface takes roughly 7 seconds to reach the submersible at the bottom of the trench. The submersible's acknowledgement or response takes another 7 seconds to return. This 14-second round-trip delay transforms what should be a conversation into an exchange of carefully composed messages, each one sent and then followed by a long pause as everyone waits to see if it was received and understood. The delay itself would be manageable if the communication channel were otherwise reliable, but acoustic signals in the trench suffer from all the same distortions that plague sonar mapping. The sound waves must travel through layers of water with different temperatures, pressures, and salinities, each one bending the signal path and reducing its strength. They reflect off the trench walls, the surface, the seafloor, and any suspended particles in the water, creating echoes and reverberations that overlap with the original signal and make it difficult to decode. The bandwidth of acoustic communication is severely limited compared to radio, measured in bits per second rather than megabits or gigabits. This means that only the simplest messages can be sent: short text commands, basic telemetry data, occasional status updates. There is no possibility of streaming video from the submersible to the surface in real time, no way to send detailed images or complex data sets until the vessel returns and can be physically connected to computers. These limitations create profound challenges for remotely operated vehicles, or ROVs, which are controlled from the surface by pilots who watch video feeds and manipulate joysticks to steer and operate mechanical arms. In shallow water, ROVs are connected to their support ship by a tether, a thick cable that carries both power and communication signals. The tether allows real-time control with minimal latency, and the continuous power supply means the vehicle can operate for hours or even days without concern for battery life. But in the Mariana Trench, the tether becomes a vulnerability rather than an asset. An 11-kilometer cable must be enormously strong to support its own weight without breaking, yet also flexible enough to spool and unspool smoothly. It must be armored against abrasion and pressure, yet not so thick and heavy that it becomes impossible to deploy or creates excessive drag that the ROV cannot overcome. Currents in the water column, though often slow, can catch the tether and pull it sideways, creating tremendous tension. The cable, hanging like a massive fishing line from the surface, acts as a sail, and even gentle currents can generate forces strong enough to drag the ROV off course or prevent it from moving in the desired direction. If the current is strong enough or the cable becomes snagged on a feature of the trench wall, the tension can exceed the cable's breaking strength and the tether snaps, instantly transforming the ROV into an unrecoverable piece of expensive debris that will remain on the seafloor forever. Even without breaking, a tethered ROV in the trench is always fighting against the pull of its own cable, using energy and thruster power just to maintain position rather than for exploration. The pilot on the surface, watching delayed video feeds and issuing commands that take seconds to execute, must constantly anticipate where the vehicle will be rather than responding to where it is. A cognitive challenge that requires immense skill and patience. Autonomous underwater vehicles, or AUVs, attempt to solve the tether problem by cutting the cord entirely. These robots carry their own power and operate independently, following pre-programmed instructions or making decisions based on their onboard sensors and software. Without a tether to restrict movement or transmit interference, AUVs can navigate more freely and cover larger areas than tethered ROVs. But autonomy introduces its own set of challenges, particularly in an environment as unforgiving as the Mariana Trench. An AUV that encounters an unexpected obstacle, a malfunction, or a situation its programming did not anticipate has no way to ask for help or receive new instructions. It must make decisions on its own, and if those decisions are wrong, the vehicle may become lost, damaged, or unable to return to the surface. The consequences of losing communication with an AUV are severe. If the vehicle's batteries fail while it is on the seafloor, it becomes a permanent resident of the trench, a several million-dollar contribution to the archaeological record of human exploration. If navigation systems fail and the vehicle cannot determine its position or the direction back to the recovery point, it might wander aimlessly until power runs out. If a thruster fails or a buoyancy control system malfunctions, the vehicle might sink into soft sediment and become buried or drift away on a current and surface hundreds of kilometers from the search area. Unlike a tethered ROV, which can be pulled back to the surface even if it loses power or control, an autonomous vehicle is entirely on its own once it leaves the surface. This independence is both its greatest strength and its greatest vulnerability. To mitigate these risks, AUVs are designed with multiple layers of autonomy and fail-safe behaviors. If the vehicle detects that it is running low on battery power, it automatically abandons its mission and begins the ascent to the surface. If sensors indicate a collision is imminent, the vehicle stops and attempts to navigate around the obstacle. If communication with the surface is lost for longer than a predetermined time, the vehicle assumes something has gone wrong and executes emergency procedures. These behaviors are programmed before the dive and cannot be changed once the mission is underway, which means that the vehicle's responses to unexpected situations are limited to what its designers anticipated. True intelligence, the ability to reason about novel problems and devise creative solutions, remains beyond the capability of current autonomous systems, though advances in artificial intelligence are beginning to change this. In 2025, organizations like the National Oceanic and Atmospheric Administration began developing AI systems specifically designed for deep ocean robotics. These systems use machine learning algorithms trained on vast datasets of underwater imagery and sensor readings to recognize features, identify organisms, and make decisions about where to explore and what to sample. The goal is to create AUVs that can conduct meaningful scientific exploration without constant human supervision, vehicles that can detect a chemosynthetic vent community or an unusual geological formation, and adjust their mission plans autonomously to investigate. Early tests have shown promise, with AI-equipped robots demonstrating the ability to track moving organisms, identify species from video feeds, and prioritize targets based on scientific criteria. These capabilities could transform deep ocean exploration by allowing vehicles to operate more independently and make better use of their limited time and energy at depth. But even the most sophisticated AI cannot overcome the fundamental communication barrier. An autonomous vehicle might be capable of making intelligent decisions on its own, but those decisions and the data they are based on cannot be communicated to scientists on the surface until the vehicle returns. This creates a frustrating disconnect where discoveries are made in the depths but remain unknown to the researchers until hours or even days later when the data can be downloaded. It also means that humans cannot guide the exploration in real time, cannot say, "Look closer at that feature," or "Take an additional sample from that location" when something interesting appears in the video feed. The exploration proceeds blindly from the surface perspective, controlled by algorithms and programmed priorities rather than by the immediate judgment of experienced scientists. The low bandwidth of acoustic communication also limits what telemetry can be sent from the vehicle to the surface during a mission. A typical acoustic modem might transmit only a few hundred bits per second, enough for short text messages and basic numerical data, but wholly inadequate for images or detailed sensor readings. A submersible might send periodic status updates indicating its depth, position, battery level, and whether major systems are functioning, but these sparse messages provide only the barest outline of what the vehicle is experiencing. The richness of the environment, the details that make each dive unique and scientifically valuable, remain locked inside the vehicle's data recorders until recovery. This information asymmetry means that surface controllers are making decisions about the mission based on incomplete and delayed information, never quite sure what the vehicle is seeing or encountering in the moment. The challenge of communication extends beyond just the link between submersible and surface. Coordinating multiple vehicles operating simultaneously in the trench, which could dramatically increase the rate of exploration and data collection, requires that the vehicles be able to communicate with each other. But acoustic communication between vehicles faces all the same problems as communication with the surface, plus additional complications from the geometry. Sound waves traveling horizontally rather than vertically encounter different reflection patterns and acoustic paths. Two vehicles separated by even a few hundred meters might have difficulty establishing reliable communication if there is terrain between them that blocks or distorts the signals. The vision of a coordinated fleet of autonomous robots exploring the trench together, sharing information, and dividing tasks efficiently remains largely theoretical because the communication infrastructure needed to support such operations does not yet exist in a form that is practical or reliable at Hadal depths. Some researchers have experimented with hybrid approaches that combine elements of tethered and autonomous operation. A vehicle might be connected to the surface by a very thin fiber optic cable that provides high bandwidth communication without the weight and drag of a traditional power tether, while the vehicle relies on its own batteries for propulsion. The fiber optic link allows real-time video transmission and control with minimal latency, giving operators a much clearer picture of what is happening at depth. But fiber optic cables are fragile, easily broken by tension or abrasion, and deploying them reliably to extreme depths remains technically challenging. The cable must be managed carefully to prevent tangling or excessive tension, and even minor damage can sever the connection completely, transforming the mission from tethered to autonomous instantaneously. The isolation imposed by poor communication creates psychological challenges as well, particularly for human-occupied submersibles. The crew inside the pressure sphere knows that if something goes wrong, if systems fail or the vessel becomes trapped, communication with the surface will be slow and limited. They cannot simply call for help in the way a surface vessel or aircraft could. They must rely on their own training, their own problem-solving skills, and the redundancy built into their systems to handle emergencies. This self-reliance is both empowering and sobering, a constant reminder that at the bottom of the trench, they are more alone than humans have ever been in most exploration scenarios. Even astronauts on the International Space Station, orbiting 400 kilometers above Earth, have better communication with mission control than a submersible 11 kilometers below the ocean surface. The communication barrier also affects how quickly new discoveries can be shared with the world. When a spacecraft transmits an image from Mars, it can be on scientists' screens and then shared with the public within minutes or hours. But when a submersible captures remarkable footage at the bottom of the Mariana Trench, that footage remains inaccessible until the vehicle surfaces is recovered and its data storage devices are physically connected to computers. This delay means that the immediacy and excitement of discovery, the ability to share findings as they happen, is lost. The exploration of the trench is documented and studied, but it unfolds in a kind of time-shifted manner, with the most important moments only becoming known long after they occurred. This is changing slowly as technology improves, but the fundamental constraint that electromagnetic communication does not work underwater and acoustic communication is slow and limited ensures that the trench will remain a place of delayed revelation, where what is discovered in the depths is only fully understood and appreciated after the explorers have returned to the surface. This delay means that the immediacy and excitement of discovery, the ability to share findings as they happen, is lost. The exploration of the trench is documented and studied, but it unfolds in a kind of time-shifted manner, with the most important moments only becoming known long after they occurred. This is changing slowly as technology improves, but the fundamental constraint that electromagnetic communication does not work underwater and acoustic communication is slow and limited ensures that the trench will remain a place of delayed revelation, where what is discovered in the depths is only fully understood and appreciated after the explorers have returned to the surface. Yet, despite all these barriers, despite the crushing pressure and absolute darkness, despite the cold that drains batteries and the isolation that cuts off communication, despite the geological restlessness and the tyranny of limited energy, human curiosity continues to push back against these obstacles. The question is not whether we will explore the Mariana Trench more completely, but how quickly technology will evolve to make that exploration practical, safe, and scientifically productive. The recent achievements in trench exploration suggest that we are entering a new era of capability. Between 2021 and 2025, the MEER project demonstrated what sustained, systematic effort can accomplish, even within the constraints we have discussed. Chinese researchers conducted 33 dives to depths ranging from 6,000 to nearly 11,000 meters, collecting 1,648 sediment samples that together represent the most comprehensive biological and geological survey ever undertaken in a Hadal environment. The Fenduje submersible, purpose-built for these missions, pushed the boundaries of what deep diving vehicles can achieve. Its ability to carry 220 kilograms of samples, more than any previous Hadal submersible, meant that each dive could bring back substantial material for analysis. Its 6-hour operational window at maximum depth, enabled by sophisticated thermal management and efficient power systems, provided enough time to conduct meaningful scientific work rather than merely touching the bottom and rushing back to the surface. The discoveries from these expeditions have been transformative. Of the 7,564 microbial species identified from the samples, 89.4% were completely new to science, genetic lineages that had never been cataloged or studied. This is not a small addition to our knowledge of life on Earth, but a wholesale expansion of the tree of life, revealing entire branches of evolution that had remained hidden because they exist in a place humans could barely reach. Even more remarkable was the discovery in March 2025 of a thriving chemosynthetic ecosystem at depths approaching 11,000 meters, the deepest such community ever documented. These organisms do not depend on sunlight or on organic matter raining down from the surface. They build their entire existence on chemicals seeping from the Earth's crust, hydrogen and methane and sulfur compounds that provide energy for bacteria, which in turn support more complex life forms. The existence of such ecosystems fundamentally changes our understanding of the limits of habitability, suggesting that life may be far more widespread in extreme environments than we previously believed. China's broader deep ocean program has also achieved milestones that seemed impossible just a decade ago. By 2024, Chinese submersibles had completed manned dives to the deepest points in all 8 major Hadal trenches around the world, a feat of engineering and logistics that required coordinating expeditions across vast distances and varying conditions. These dives established multiple world records for depth, duration, and sample collection, demonstrating that regular access to the Hadal zone is no longer a theoretical possibility, but a practical reality for nations willing to invest in the technology and training required. The knowledge gained from these missions, the samples collected, and the experience accumulated by crews and support teams represent a foundation upon which future exploration can build. turning what were once extraordinary expeditions into routine scientific operations. Yet these achievements, impressive as they are, have only scratched the surface of what remains to be learned. The Mariana Trench stretches for over 1,500 miles, and the area actually explored by submersibles amounts to a few dozen sites, tiny spots of illumination in a vast darkness. The samples collected, though numerous, come from a minuscule fraction of the available habitat. The organisms filmed and photographed represent whatever happened to be visible within the narrow range of the lights at the specific locations and times the submersibles were present. For every question answered, the MEER project raised dozens more, revealing complexity and diversity that demand further investigation. This is the nature of exploration. Each advance expands the boundary of knowledge, but also expands our awareness of how much remains unknown. The future of trench exploration will likely be shaped by several technological advances that are already emerging from laboratories and engineering centers around the world. Artificial intelligence, as we have seen, is beginning to enable autonomous vehicles to make intelligent decisions about where to explore and what to investigate. The systems being developed by NOAA and other organizations in 2025 represent only the beginning of this capability. As machine learning algorithms become more sophisticated and are trained on larger data sets of deep ocean imagery and sensor readings, they will become better at recognizing features of interest, identifying species, detecting chemical or thermal anomalies, and adapting mission plans in real time. Future AUVs equipped with these systems may be able to conduct exploration with a level of independence and judgment that approaches or even exceeds what human pilots can achieve, operating for weeks or months at a time and covering far larger areas than any human-occupied submersible ever could. Advances in materials science are producing alloys, composites, and ceramics that offer better strength-to-weight ratios, improved resistance to corrosion and fatigue, and more predictable behavior under extreme pressure. Some experimental materials being tested in laboratories can withstand the forces at the bottom of the trench while being significantly lighter than the titanium and steel currently used, potentially allowing future submersibles to carry more payload, more instruments, or larger battery banks within the same overall weight budget. Carbon fiber composites, which have revolutionized aerospace engineering, are being adapted for deep ocean applications, though the challenges of ensuring uniform quality and preventing water ingress into the composite structure at extreme pressures remain significant. Ceramic materials, which are inherently resistant to compression, offer another avenue for innovation, though their brittleness and difficulty of fabrication have so far limited their use. Battery technology continues to advance, with new lithium chemistries and solid-state designs promising higher energy densities and better performance at low temperatures. A battery that can store 50% more energy in the same volume and weight, or that maintains 80% of its capacity at near freezing temperatures instead of 50%, would transform the economics of deep diving by extending mission durations and reducing the need for thermal management. Researchers are also exploring alternative energy storage technologies, including high-pressure hydrogen fuel cells and even mechanical energy storage systems that use the pressure differential between the interior and exterior of the vessel to store and release energy. None of these technologies are ready for deployment yet, but each represents a potential pathway to breaking the energy constraint that currently limits every dive. Communication technology is also evolving, though more slowly than other areas, because the fundamental physics of underwater propagation cannot be changed. Advances in acoustic modems, signal processing algorithms, and error correction techniques are gradually increasing the bandwidth and reliability of underwater acoustic links. Some experimental systems use very low-frequency sound waves, which can travel farther through water but carry even less information, to establish basic connectivity that can be augmented with higher frequency bursts when conditions allow. Others explore optical communication using blue-green lasers that can transmit data at high rates over short distances through clear water. While optical links cannot replace acoustic communication for long-range connectivity, they could enable high-bandwidth data transfer between vehicles operating in close proximity, allowing coordinated swarms of robots to share information and work together more effectively. Perhaps most intriguingly, there is growing interest in developing fleets of small, relatively inexpensive autonomous vehicles that could be deployed in large numbers to conduct distributed exploration. Instead of sending a single, large, capable, and extremely expensive submersible on a few carefully planned dives, future missions might release dozens or even hundreds of smaller robots that spread out across the trench, each one exploring a different area and collecting different data. Some of these vehicles might be disposable, designed for a single mission and not expected to return, with their data transmitted acoustically before their batteries fail. Others might be recoverable, surfacing at predetermined times or locations to upload data and receive new instructions before diving again. This swarm approach could provide the broad area coverage that is currently impossible with traditional submersibles, filling in the blank spaces on our maps and revealing patterns and features that only become apparent when large regions are surveyed simultaneously. These technological advances will not eliminate the challenges we have explored throughout this journey. Pressure will still crush, cold will still drain, darkness will still conceal, and energy will still be finite. But each improvement, each incremental gain in capability makes the trench slightly more accessible and slightly less mysterious. The process is gradual, frustratingly slow compared to the pace of progress in other fields, but it is real and it is accelerating. The Mariana Trench of 2025 is more explored, better understood, and less alien than the Mariana Trench of 2000, and the Trench of 2050 will be even more so. The question is not whether we will eventually achieve comprehensive exploration of the deepest ocean, but how many decades or centuries that achievement will require and what we will learn along the way. Yet even as technology advances, it is worth remembering why the Mariana Trench remains so difficult to explore. It is not because the trench is actively resisting us or because nature is deliberately placing obstacles in our path. The trench is simply being itself, a place shaped by physical processes that have operated for millions of years without any need to accommodate human curiosity. The pressure exists because water is heavy and 11 kilometers of it weighs an enormous amount. The darkness exists because water absorbs light, and 11 kilometers is too far for photons to travel. The cold exists because the deep ocean is isolated from solar heating and because cold water is denser and sinks. The geological restlessness exists because tectonic plates are in motion, and the trench is where they meet. None of these phenomena care about our desire to explore or our frustration with the limitations they impose. They are simply the natural state of the deepest ocean. Understanding this is important because it shapes how we approach exploration. The trench is not an adversary to be conquered through brute force or overwhelming technology. It is an environment to be understood, respected, and negotiated with on its own terms. Every dive is a conversation between human ambition and physical reality, a delicate dance where we push the boundaries of what is possible while accepting the constraints that cannot be changed. Success comes not from fighting against the trench's nature, but from working within it, designing systems that can survive and function in extreme conditions by accommodating rather than resisting the forces at play. The most effective deep-sea vehicles are not the ones that try to overcome pressure with ever thicker walls, but the ones that distribute pressure evenly and use geometry to turn a crushing force into a strengthening one. The most productive missions are not the ones that try to stay at depth the longest, but the ones that use their limited time most efficiently. This philosophical approach, this acceptance that exploration is fundamentally about adaptation and understanding rather than conquest and dominance, may be the most important lesson the Mariana Trench has to teach us. In an era when technology seems capable of solving any problem and reaching any destination, the trench remains stubbornly difficult, a reminder that some places demand humility and patience. It reminds us that Earth still holds frontiers as challenging as any in the cosmos, that we do not need to look to other planets to find worlds that test the limits of human capability. The alien landscapes we dream of exploring on Mars or the moons of Jupiter exist here, hidden beneath our own oceans, waiting for us to develop the wisdom and technology to visit them properly. The fact that 95% of the ocean remains unexplored is both humbling and exciting. It suggests that we are still in the earliest stages of understanding our own planet, that there are vast reservoirs of biodiversity, geology, and phenomena that we have barely begun to investigate. The Mariana Trench is not unique in its resistance to exploration. It is simply the most extreme example of a much broader challenge. Thousands of seamounts, countless kilometers of mid-ocean ridges, entire abyssal plains covering areas larger than continents, all remain poorly studied or completely unknown. The techniques and technologies developed for trench exploration will eventually enable us to access these other deep ocean environments as well, slowly illuminating the largest and least known habitat on Earth. As this journey through the challenges of Mariana Trench exploration comes to a close, we return to where we began, with the recognition that the deepest place on our planet remains mysterious, not because we lack the will to explore it, but because the physics and chemistry and geology of the deep ocean create barriers that cannot be simply wished away or overcome through determination alone. Each barrier we have examined, from the acoustic distortion that makes mapping uncertain to the pressure that threatens hulls to the darkness, that limits vision to the cold, that drains batteries to the geological instability that reshapes the seafloor, to the energy constraints that limit dive times, to the communication challenges that isolate explorers. Each one is real, measurable, and rooted in fundamental physical principles. Together, they ensure that the trench remains one of the last true frontiers on Earth, a place where exploration is still difficult, dangerous, and profoundly meaningful. The story of the Mariana Trench is not finished. It is being written with each dive, each sample collected, each organism discovered, each technological advance that pushes the boundaries slightly farther. The next chapters will be written by engineers who design better vehicles, by scientists who interpret the data those vehicles collect, by software developers who create smarter autonomous systems, and by the next generation of explorers who will see challenges we cannot yet imagine and find solutions we have not yet conceived. The trench will yield its secrets slowly, revealing itself in fragments and glimpses, rewarding patience and persistence. And in doing so, it will continue to remind us that the greatest adventures are not always the ones that take us farthest from home, but the ones that take us deepest into the mysteries that have always surrounded us, hidden in plain sight beneath the waves, waiting in the silent darkness for those brave and curious enough to seek them out.